I'm here to represent. I'm here to represent Computer Architecture Group, and we focus on building faster, more efficient, and cooler computers. So I have two objectives. I'm echoing what Ramsey said. First, I want to convince you that you should come to Wisconsin because we are working on really exciting problems, and I believe you'll be very successful in achieving your goals in our department. Second thing that I want to tell you is what is computer architecture and why this is an exciting time to be a computer architect. So there are 6 of us in computer architecture group, and I'm going to talk about what we do and what the field is doing. So, all right. So computer architects design the hardware, and they basically make decisions how to use transistors to improve performance and energy efficiency of computers. So this all started back in 70s when Intel built their first microprocessor 4004. It was a 4-bit microprocessor, and within 3 decades, engineers built a P4 chip, which you can see here, which could be clocked at 4 gigahertz. And compared to original 4004, P4 chip was 100,000 times more powerful. And this was partly driven by innovative designs that computer architects did. And several very creative ideas that enabled this growth came out of Wisconsin. So our faculty and students at Wisconsin invented a lot of key and interesting ideas in pipelining, ILP, and that kind of created this field as a whole, right? And in early 2000s, the world switched from a single core to multi-core processor, and this was a paradigm shift. It gave us the ability to fully leverage the transistor scaling. Now, with more transistors, we could add more and more cores and build very efficient and highly parallel systems. And this transition was not easy. I mean, it had a tremendous challenges. And again, computer architects stepped in and they solved some of the key issues in cache coherence, cache design, out of order processors, and so on. And this was driven by really cool computer architecture ideas, and a lot of great work came out of Wisconsin. And this transition is still continuing. Now we have AMD's 64 core machine. We have NVIDIA's GPUs and Google DPUs. So there are even more number of processors and hardware platforms that one can use to build efficient systems. And this is very challenging because now we have these heterogeneous systems, and designing these heterogeneous systems is becoming challenging, right? So we will need a lot of creative ideas and bright minds to continue building faster and more efficient computers. This is important because this growth in hardware has truly enabled things in our day-to-day life. And with low cost and efficient hardware, now computing is touching almost every individual on this planet. From your phone to power grids and the robots and windmills, everything is driven by this hardware-software combo, right? So it's not an understatement to say that software runs the world, right? But it's changing very fast, and soon we'll see a new paradigm, or in fact, it's already here. Soon AI is going to take over. AI has already penetrated retail, healthcare, manufacturing, automobile, pharma, you name it. It's already there. It's driving the way we write. It's driving the way we write software, build hardware, and even more, right? But in order to keep growing this paradigm, in order to keep growing our AI models, we need faster and better hardware, and that because ultimately, everything runs on the hardware, right? And even more importantly, the hardware systems that we are building today, they are used by billions of people, right? And it's going to be around for decades to come. So we will need designs that are not only high performance and energy efficient, but that are also secure and sustainable. Because if we have vulnerabilities in our hardware, it's going to impact billions of people, right? So while we are thinking about building sustainable, secure, and efficient hardware, we also need to keep in mind that technology scaling is slowing down. We are not going to get much help from Moore's law. It's probably going to end soon. So we cannot really rely on transistor scaling as we did in early 2000s. So onus is completely on all of us to build better hardware and efficient software, and in fact go beyond the paradigm of conventional computing. Right. For example, now we have opportunity to explore and leverage emerging paradigms like neuromorphic computing. Paradigms like neuromorphic computing, where we can inspire from human brain to build really efficient, reliable software hardware paradigm, right? And I would say we can go even further beyond that and focus on truly truly disruptive paradigms like quantum computing that can solve hard and important problems. So what better place to do this than University of Wisconsin, because we have a strong history and culture of building innovative designs like branch predictors, out-of-order architectures, cache coherence, and memory consistency. So we have this strong history and culture, and we are going to continue working on important and interesting problems. We have a strong presence with faculty members who have been recognized for their contributions by several national and international awards. We have about 25 grad students and several well-funded projects, right? So that's great. So that's great that we have this presence. But what is it in it for you? So many of our alumni are professors at the top places in academia, and many have gone to industry and have made their mark. Right. So we have this rich tradition of working on important problems, and our alumni go to academia and industry, and they are very successful. In the last 3 years, our students have published more than 20 papers in top computer architecture venues. And we are growing, and we are excited about a lot of really interesting problems. So come join us so that we can add you to this slide. Right. So I'll briefly go over the key research directions and projects. So I'm Swamit Tanu. I work on quantum and emerging technologies. My focus is on building compilers and software for quantum computers. So quantum computers are not like a science fiction. They are here. In fact, I ran some programs on quantum computer this morning. So quantum computer you can think about quantum computers as hardware accelerators, which can solve problems that no conventional computers can solve. So there are really interesting problems that we cannot solve because of computational complexity, but some of those problems can be solved very efficiently on a quantum computer, right? So, but it's very challenging to design and build quantum computers. It needs a cryogenic environment, and there are lots of cool architectural problems there. So I'm excited about building quantum accelerators. Professor Sankarlingam is focusing on building programmable accelerators. So we have this problem of programmability when we are talking about accelerators, hardware accelerators, and Professor Sankarlingam wants to break this programming wall to truly democratize the compute opportunities. Right? Previously, he has worked on stream data flow acceleration, and now he is looking at how we can build more sustainable and programmable accelerators. Professor Sohi has done a lot of work in out-of-order architecture, speculative multithreading in the past. Now he's focusing on non-traditional multi-core architectures, and he's also looking at several interesting problems on how to better program this multi-core paradigm and how to build secure architectures. Right? So yeah, in the other side of our building, Professor Lipassi, who is in electrical and computer engineering, he is focusing on how we can scale the multi-core processors with more power-efficient cache coherence and interconnect designs. He is also focusing on non-von Neumann and biologically inspired computing systems. And there are some really cool projects going on in his group, right? So Professor Sinclair, who heads the HAL group, is working on cache coherency, consistency, data organization in heterogeneous parallel systems. They are doing really amazing work on building optimization tools for hardware, software, and emerging applications. Right. So some of Matt's work is really interesting. You should take a look at his recent papers, and I'm sure that you'll find some really cool ideas there. Joshua San Miguel, who is an Ece faculty, he looks at approximate computing, building really efficient systems that we can deploy in in a low energy setting where you can harvest energy from the environment and build intermittent computing systems. Again, there are tons of cool ideas that Josh is working on, and all of us are really excited that you're here, and we look forward to seeing you at Wisconsin. So please do check out, this is the webpage for our architecture group, and please reach out to any of the faculty. We would be happy to answer all your questions. Thank you.
Thank you, Swamit. And next up, we have, with a little extra time you've given him, Shivaram Venkataraman, representing the systems group here at Madison.
I'm just figuring out how to make Zoom get to the right screen to share. Can everybody see this?
Yes.
All right. Thank you very much. Thanks, Angela, for the introduction. Thanks, Swamit, for the extra 3 minutes that I get to talk more. And thanks all for being here and attending this. I really appreciate it, given that everybody's spread out across different time zones. So this might be the middle of the night for you, or this might be super early in the morning. And we're really excited to have you all be here. So I'm Shivaram Venkataraman, and today I'm going to be talking about the systems group here, which we have sort of branded ourselves as MAD Systems, as the website there below says, right? So the talk is going to be structured in two parts. The first part, I'm going to briefly tell you about what is systems research, right? And what are the kind of problems, or what are the kind of technologies that get built as a result of doing systems research. This is to inspire some of you who may have an open mind in terms of what areas you want to work on, right? To be motivated to work in systems, right? And in the second part, I'll give you a brief overview of systems research at Wisconsin, right? Which will ground you in what all of the faculty here and also the students here are working on. Right? All right, so let's start by talking about what is systems research, right? So systems research has a long history as well, right? It goes back probably to the late 1960s with early operating system design done by really esteemed folks like Dijkstra, right? And I think Dijkstra wrote this, he called it a multi-programming system, which these days we would call as an operating system, which was called that was the name of the system, right? And so there was some early identification that there is a need for developing systems that is actually it's very intellectually challenging to do this and to do it well, right? There's a lot of work that came following the early work by Dijkstra and others. And one of the things I always like to stress, in case if you haven't read this is a very good article to read from Butler Lamson, written in the 80s, right, on what are the aspects that make up a computer system design, right? And I think this article makes this very good point that designing a computer system is very different from, let's say, designing an algorithm, or because you have to reason about things like what is the interface that my system has, right? And who are the users going to use it, right? So it's less precise, more complex, and also you have to design the internal structure of these systems, right? And also the interfaces between various structures, right? So system design has a lot of such concerns about like designing the appropriate interface and the appropriate structure, right? To get to some measure of success, which also varies based on the system, right? A lot of times our measure of success is performance, but also you could have reliability or you could have usability. Success here is a very multidimensional kind of requirement, right? So, so this is a brief overview of what is like designing computer systems, right? And you might be wondering, so what has some of the systems that or software that I might be using that's influenced or come out of like computer systems, academic computer systems research, right? So this list is very long. I'm giving you my biased subset of things that I think are influential projects that came out of doing computer systems research, right? Probably the one that most of you are most familiar with must be the Unix operating system and the C programming language, right? Designed in the mid 70s by folks at Bell Labs, right? This was an early publication in sort of the computer systems journal that was there at that point, was the design of the Unix operating system, right? I think we still read it in some of the advanced operating system courses out here, right? And then there was a lot of follow-up work on operating system development, right, which came out of following Unix that was also a part of like the systems research domain. There's also been a huge tradition of like storage systems and file systems that have been built through systems research contributions. Many of you might have used like a network file system like Sun NFS, or maybe some of you have used like an Andrew file system, right? Also systems projects that did research into how do we sort of build widespread distributed storage systems, right? And also more recently, things like NetApp, which is a company that some of you might have heard of, that produce like big distributed file system boxes, as shown out here in the figure, right? These also came out of like influential systems research done in the mid 90s into this file system called Waffle, a very nice name for a file system, right? That was done as a part of the computer systems research. Fast forwarding a little bit more, the idea of virtual machines, which we kind of like take for granted now, right? Many of you might have used VMware or like other kind of virtual machine installations, right? There was a lot of systems research that went into developing these technologies and in making them really efficient, right? To be able to run Windows on your Mac or to run, Linux on your, Windows machine and so on and so forth, right? And some of these big projects also that you might recognize include the Zen project that was, again, a very hallmark sort of like systems research result that was in the early 2000s, right? So far, I've traced a journey from, sort of operating systems, storage, and virtual machines, right? As you might be aware, these days, computers are no longer single boxes, but they're huge clusters of boxes, right? That are laid out in complex layouts with colorful cables, as shown out here, right? And this era of kind of like huge cluster-based computing or data center-based computing has also led to the development of very influential systems research and in terms of the software and the technology that drives them, right? Some famous systems that you might have heard of that came out of the folks from Google include like the Google file system and the MapReduce programming framework, right? That enable users to store data and then process data on these really large scale cloud computing kind of installations, right? Fast forwarding a little bit more to the most recent decade that went by, right, where systems started really specializing towards the kind of workloads that were dominating, many different enterprises and industry, right? Especially this idea of like data analysis and data processing of large scale structured and unstructured data has taken hold as a very important workload, driving a lot of enterprises in the world today. And this led to the creation of systems like Apache Spark, which was again developed inside the systems research domain around like 2010 and 2012, right? And in case you've been sort of like under a rock and haven't heard, machine learning is sort of a big deal these days, right? With many different applications being powered by machine learning models. I'm pretty sure your mobile phone probably has like a dozen or so machine learning models running on it doing various things, right? And so training these machine learning models and serving these machine learning models efficiently, right, has become a really big concern. And there's been a lot of influential systems research that has come to sort of tackle this problem, right? One of the frameworks that you might identify is probably TensorFlow, which was a research paper published at OSDI in like 2016, right? So this is an example of that. And of course, there are many more frameworks and many more technologies also coming out of systems research to support this, right? So overall, hopefully by now you would have been convinced that systems research has really contributed to a lot of the software that you use and kind of like take for granted today, right? And has had major impact in terms of like how people use computing, right? So you might be wondering, okay, so it looks like people have done everything there is to do in systems research, right? So what is new to do in systems research? And like, if you become a graduate student, if you, let's say, start your PhD tomorrow, right? What are some cool problems you can work on, or sort of what is new in systems research? So I like to always think of systems research as being like sandwiched between like two areas, right? Also, I have to say, box diagrams like this are very, very common in systems, So, so systems research is in the middle between hardware and applications, right? So you just heard this talk from Swamit about all of this cool new hardware coming out, including everything ranging from like, heterogeneous computing to like quantum computing and like other kind of like groundbreaking technology, right? And every time there's some new hardware devices that come out, there are automatically systems questions that come in terms of like, how do we kind of like build a programmable user interface to this particular hardware? How do we kind of build efficient and reliable systems to run on this hardware, and so on and so forth, right? So that's this bridge between systems and hardware that constantly keeps reinventing itself over and over again. Right? The other interesting reason why there's always cool new problems to work in systems research is in the upper box, which is applications, right? So, so by that, I mean, for example, when machine learning became this very important application domain, right? This led to the development of a lot of cool new systems research in order to effectively support these workloads in various different contexts, right? So, so there's always cool new problems to work in systems because the applications and the hardware are constantly evolving as we keep going along, right? So let me give you a few examples. I probably briefly touched on them in the previous slide as well, right? So on the application side, you have kind of like many of these trends which are becoming like prevalent in many parts of the world, right? So one is you have a lot of like edge devices or these kind of IoT devices. I've shown like a traffic camera there, right? Which are used for like various applications, like, detecting collisions or like, ensuring like traffic safety and things of that sort, right? And these pose a lot of new interesting system challenges in terms of like, how would you actually deploy software? Would you like go and put it on every camera or like every kind of like device that exists at a traffic light, right? That sounds expensive, which means that there's a lot of system design in terms of like, how do we make this efficient and also like cost effective? The slide below that is a picture below that is showing a self-driving car or a mock-up of a self-driving car, right? And there's a lot of interesting machine learning research that is making self-driving cars possible, right? But as a consequence of that, there's also a lot of new systems problems in terms of how do we handle this volume of data, right? how do we kind of ensure reliable systems that, especially in this kind of a mission critical setting, operate without failure, right? All the open problems that I think are waiting to be solved by young and new systems researchers like you. And on the right side, I'm showing some examples of new hardware. I briefly talked about accelerators. I think Swamit talked a little bit about accelerators. TPU is an example of an accelerator. But there's also new storage devices like non-volatile memory and things like that are also going to change the way we build systems. Okay, so hopefully by now you're inspired that systems research is the coolest thing in the world for you to do, right? So let me talk a little bit more about our group here at Wisconsin. We have 5 faculty as shown here in the slide, and we work on a number of different areas related to systems. Right? Ramsey briefly talked about this website, csrankings.org. His data was a little stale, right? There was some consistency issues in his data. We are actually number 2. I looked this up yesterday, on the systems rankings, right? And as you can see, I think Ramsey briefly mentioned this. We are one of the centers we have 6 faculty in systems, and then we are number 2 out here, right? So there's a very effective rate of like how student-faculty collaboration goes on, and our research is really impactful as shown by this, right? So this is one of the top places to do systems research without any doubt, right? And some examples of the kind of like topics and papers that systems students work on, right? This is a very recently biased sample of like some paper titles that I pulled up, right, from across the group. And as you can see from this, there's not the things I would like to point out here is that the topics range across a different number of layers, right? So there are students who work on like terabyte scale memories and persistent memories, right? There are students who work on machine learning systems, right? In terms of gradient communication. And then there's also work going on in terms of like, how do you sort of remedy performance issues and performance modeling in like various CPU, GPU, and different kinds of applications, right? So our students do a really amazing research, and as a result of that, I think Ramsey also talked a little bit about how they go on to become, either academics as Vijay and Ying are, or into positions in various industries, right? All the research labs have some of our alumni. Also, some of a bunch of the startups have our alumni. And one of the cool things that we recently did was try and make a list of all our alumni and where they are. So take a look at our website, and it might be interesting for you to peruse through our list of alumni going all the way back to the 80s, right? Yeah. Just to give you an idea of or a sampling of a few projects that go on, right? As I mentioned before, our faculty really work across all the layers of the system stack, right? Starting from a single node, like persistent memory or like accelerators and how they interact with the operating system, right? Going all the way up the operating system stack to distributed systems, cluster scheduling, and onto the applications domain like machine learning or SQL and so on, right? Here's a sampling of a couple of projects, right? You can, of course, look up more stuff, and we'd be happy to chat more about this in our one-on-ones, right? So there's a lot of work going on in storage systems. We are one of the top storage system research groups in the world, right? And these range from like integrating new devices like flash, persistent memory, to like reliability, consistency, and so on. There's a lot of exciting work happening in this area of what I like to call as systems meets machine learning, right? I have a bunch of projects related to how do you sort of scale these machine learning workloads and manage clusters which are running like a large number of machine learning workloads, and also projects which relate to how do you look at machine learning workloads in new domains like graph learning and things like that, and build scalable systems for that. And more recently, there's also this series of projects on how do we use machine learning to also further improve systems, right? So I like to think of it as a symbiotic relationship between systems and machine learning, kind of going back and forth, right? So it's a lot of interesting projects in that area as well. And finally, we do a lot of work in the context of like large-scale computing installations, be it like supercomputers, be it large-scale data centers, right? And again, looking across the stack here in terms of like be it from high performance networking to performance profiling and instrumentation of like various binaries running in these like large installations, right? To looking at specific applications and their challenges like stream processing or other big data analytics workloads, right? I noticed that I have 1 minute left, so I'm going to put up this last slide. So please come and meet us, ask us more questions. We're always happy to talk to students. I guess most of you have one-on-ones with us this afternoon and tomorrow morning as well. Also talk to our students. They're really awesome. They have put together a couple of these open houses later today and also early tomorrow morning to handle various time zones, right? And hope to see you all in Madison. With that, I'll end and hand it back to Angela.
Thank you, Shiv. Appreciate your presentation. Next up is Professor Stephen Wright from the Optimization Group.
Okay, I hope you can hear me.
Everybody's at the lake today.
Yeah. Yeah, it's sunny outside, so that's what we like to fantasize about, being down on the terrace. All right, well, welcome everyone. So I'm Steve Wright from the Optimization Group. We have a thriving optimization group here in Madison that several of us are in computer science, but it also spreads across various other departments. So I'll tell you a little bit about the kinds of projects that we do and things that we're currently involved in, and then I'll tell you a little bit about the different group members. So what is optimization? Probably many of you haven't had much acquaintance with the area. It's kind of a mathematical computational area where we try to come up with techniques or algorithms for optimizing the performance of certain systems, subject possibly to some constraints on the choices that we can make. And I've just got a very small sample that I came up with about 3 minutes ago of possible areas where optimization problems arise. So one that's very much in our mind these days is extracting meaning from collections of data, and that's something I'll say a little bit more about in the next few slides. Another area is logistics and operations in manufacturing. If you've got manufacturing processes going on, you want to optimize the way you use resources. If you're distributing some product across the country or across the world, there are lots of optimization problems associated with how you do that in a way that meets demand and minimizes cost and so on. All sorts of engineering processes ranging from the control of a jet airplane to the control of a hydrocarbon plant need optimization problems to be solved on the fly to do effective control of these systems. Many of us here in Madison are involved in electrical power systems work, where we use optimization heavily in regulating and figuring out how to sort of design the power grid and to optimize the way plants are brought online to meet demand in real time. And a bunch of others here: engineering design, computational chemistry, structural biology, computational economics. These are all things that our group has worked on in just very recent years. So one area where optimization is very big these days is in data analysis or machine learning or AI, all of these sort of overlapping areas. And very often the sort of problem we want to solve, the optimization problem, is derived from statistics. So statistics has a way of viewing these problems and figuring out how you sort of extract meaning from data and then use that meaning to go ahead and make predictions about future data. But when you write down those statistical principles, very often the thing you have to solve in order to actuate that is an optimization problem. And the optimization problem has this form that you want to agree with the data, you want to come up with a model that agrees with the data, but also in some sense is the simplest possible explanation of the data, of the observations. So there's this old principle called Occam's razor, which basically says this. It says if you've got a whole bunch of ways to explain some phenomenon, the simplest way is probably the most likely to be correct. So you see this sort of principle over and over again in formulating data analysis problems as optimization problems. One very concrete example of this is in deep neural nets, and many of you have heard of this by now. in a deep neural network, you've typically got a bunch of data items, each of which has some label. And you've got to train the neural network to take in the item X as input and produce some desired output Y. And you have to do this for possibly millions or billions of instances of X and Y. And so what have you got to, how do you design the network? You've got to choose the weights in the network. They're the sort of numbers associated with each of those black lines that takes one node to the next. You've got to figure out how to choose those weights so that when you input X, it gives the desired output Y. And that turns out to be a huge optimization problem where the unknowns or the variables are the weights on the edges or the black lines there. And the objective is making sure that the Y that comes out of the net actually matches the version that you want. And so people use gradient or stochastic gradient type methods to solve this problem. It's a massive computational problem. People have these collections of thousands of GPUs running for weeks to solve these on real instances. There's still a lot, even though people have been doing this for years now, there's still a lot that we don't know about why optimization algorithms work so well on these problems. In fact, we started a study group yesterday where we're trying to understand better why stochastic gradient actually converges. If the network is big enough, it actually gives you the right answer. You know, that's kind of shocking because it violates several principles in optimization. So this is still a very current area of study. More broadly, this area of optimization and data analysis, there's a whole variety of optimization algorithms. I mentioned a few of them here that crop up in machine learning and data analysis. In fact, I have a book coming out with a collaborator from Berkeley who used to be in our group here. And I wanted to put the cover up because we just got the design this week. So I'm very excited about, particularly about this cover, and I guess about the book too. All right, so we do have a lot of activity going on in Madison in this general area of foundational data science. So by foundational data science, I mean the basic statistical, mathematical, computational building blocks of the area. The algorithms, the principles that underlie data analysis, and so on. And in fact, we have this institute called IFDS, Institute for Foundations of Data Science, and there's the website, ifds.info. Please take a look. And it involves about 25 faculty here in Madison, several postdocs. I think we have 4 at the moment, and a bunch of grad students. Every semester we fund 8 grad students to work in this area. And IFDS also involved teams at Washington and Santa Cruz and University of Chicago. And it involves, here in Madison, it involves people not only in computer science, but also in statistics, mathematics, electrical engineering, and industrial and systems engineering. So here is a project that one of our group members, Professor Ferris, is involved with right now. And that is in COVID vaccine allocation and distribution in Wisconsin. So he started doing this in December, and the problem is that every week, Wisconsin gets a certain allocation of the Pfizer and Moderna vaccines, and starting next week, we're also going to be getting the Johnson & Johnson vaccines. And so the problem is we've got this allocation, we get a number, I think it comes in on Sunday, and we have to figure out how to distribute it around the state. And first of all, there are fairness implementations. Decisions are being made at the state level about how much to allocate to different groups in different parts of the state. And there are constraints on how you can do the distribution because, as you know, the Pfizer vaccine requires ultra cold temperatures, and there aren't that many places where you can store, that have the facilities to store the Pfizer vaccine. And so you have to ship it to certain places indicated by those green crosses where it can be stored, and then it can be shipped out locally from each of those hubs. So every Sunday, Professor Ferris has to get the data and work with the Wisconsin Department of Health Services and the National Guard to figure out how to distribute the data around the state. And he's been doing this since December. We're very proud of the work that he's putting in here. It's a quite complicated optimization model. It involves sucking in a lot of data. He's got to work with a lot of spreadsheets, and there's a lot of fundamental algorithmic stuff going on under the covers. So he continues to do this, and we're, as I said, we're very proud of his important work on this problem. So a little bit about our faculty. These are the faculty in optimization that are affiliated with computer science. So these are people that you could sign up to do your graduate work with. 3 of us actually have our home appointments in computer science. That's Elena, Daikon, Michael Ferris, who I just mentioned, and myself. And then there are faculty in ISYE, Alberto Del Pia, Jeff Linderoth, Jim Ludke, and Rob Nowak in electrical engineering. They all have affiliate appointments in computer science. And so they're eligible to advise theses and so on in this area. So during normal times, which is, up until a year ago, we all had offices, not only, some of us had offices in computer science, but also in the Wisconsin Institute for Discovery, which is right across the street from computer sciences. And so we often hang out on the 4th floor up there. And there are many other faculty in Madison with optimization interests who you could potentially talk to if you get really interested in this area. And I've listed some of them here: Tom Rutherford in Ag Econ, Victor Zavala in chemical engineering, Lena Roald in ECE, who does power system stuff, Vivek Patel in statistics, but he does a lot of optimization too, and Carla Maccini in industrial engineering. Okay, so this is a picture of the Discovery Building, which is across the street from CS. This was a design drawing that was drawn before the building was actually built, but it actually does look like this. The only difference from real life is where all the people are standing in the foreground, that's now been replaced with Union South. And so, you wouldn't get this view anymore because it would be blocked by Union South. And computer science is off to the right there. Okay, a few words about, in the few minutes I have left, about different members of our group. Professor Ferris, he's interested in many things: decentralized control, equilibrium. These problems show up a lot in economics. He's interested in energy systems, particularly power systems. So issues like renewable energy and how that can operate on the grid in a reasonable way. He's done a lot of work with the agricultural and environmental people in the university in managing fish habitats and dealing with issues related to the dairy industry. And he also does work on multi-period stochastic optimization. And as I said, right now he's working on this distribution problem associated with COVID. So Steve Wright, that's me, and I work mostly in nonlinear optimization algorithms. I like to work in the fundamentals, but much of what I've been doing the last few years has been motivated by problems in data science and machine learning. I also work on a lot of applications problems in climate science and engineering and many other areas, chemistry and structural biology and so on. I like working on application stuff. And I also work a bit with software, so actually implementing algorithms and so on. And also numerical things that are not necessarily optimization. I have an interest in that as well. Elena Daikon, she just joined us last year, and she works on large-scale continuous optimization problems. She's also motivated by problems that come up in machine learning. She likes to take a dynamical systems perspective. She has a particular way of viewing and designing and analyzing algorithms that's sort of a little bit sort of novel and unique and so on. Gives her another set of tools she can bring to the area. She's also interested in sampling algorithms, where you're trying to estimate things like integrals from a high dimensional distribution, and applications in areas like networking and machine learning. Rob Nowak, who's our colleague in electrical engineering, he's a very distinguished person in the area of machine learning, and he is interested in optimization problems that crop up in that area. And his background was in information theory and signal processing. Jeff Linderoth, he's the chair of industrial and systems engineering. He does work in nonlinear and linear integer optimization. So these are problems where some of the variables that you want to optimize are not real numbers, they're integers, and these are actually quite surprisingly hard problems. Jim Ludke works in stochastic optimization, also does integer programming and a bunch of applications, particularly in energy. And Alberto Del Pia, his home department is industrial engineering, although, as I said, he has a courtesy appointment in CS. He also does integer programming, probably a bit more theoretical than Jeff and Jim. So he looks at complexity issues and combinatorial optimization and so on. These are our core courses in optimization. We have an undergrad course 524 that I teach right now. and that sort of teaches you how to model real world problems as optimization problems. Also linear programming. We've got a roster of courses at the graduate level, 2-semester sequence of courses in nonlinear optimization, convex analysis, and integer programming. And then there are a lot, actually more than what I put here. There are a lot of related classes in which optimization forms a component. In fact, I use some of my textbooks in those other classes that I mentioned. Okay, that's it. So welcome. I hope you all come. I'm going to be meeting some students from 3 to 4 today, but there are a couple of shared slots available still. So feel free to sign up if you still want to do that. Thanks.
Oops, I did it. I was muted. Thank you, Steve. Next up,
Sure.
Erlance Hernandez, and just let him in.
Yeah, I'm here. Can I share
Perfect.
the screen?
Yes, we can see you. Take it away.
Okay, let's see.
In a secure location, right?
Yeah, well, this location is undisclosed at this point. So
it looks like you're in Mars, Erlance. So you know.
it is, or it could be somewhere on Earth. It's,
He's in security.
let me see. So is this projecting?
Yes.
Okay. Well, good morning, everyone. My name is Erlance. I'm one of the security professors in the Madison group. That's short for Madison Security and Privacy. Congratulations on your admission. We are all very excited, at the potential of having you join us. So today I'm going to kind of talk about security and briefly overview some of the interesting projects we have been pursuing, in the past, currently, and maybe in the future. So before I jump into those results or those projects, we know at this point that computing has kind of evolved beyond these traditional use cases, of storing information, computing on information. They now enable many things in our lives. Your car is a computer with wheels and an engine. Your fridge is a computer that keeps things cold, and your ATM is a computer that dispenses money, right? And so as computers kind of play an increasingly critical role in kind of the human experience, it becomes extremely important to secure all of this new infrastructure, right? And so computer security, fundamentally deals with this idea of understanding and improving the behavior of all of these computing technologies, when adversaries are present. Okay, and this is fundamentally different from this, other notion of robustness, where we try to build systems that are robust to natural failures. Here, there is an intelligence that is actively trying to, break the system. Okay, and so let's take a case study where our group has been very active, right? And also, in any talk these days, I must absolutely mention machine learning, otherwise it is incomplete. So I chose to take this head on and, in fact, make that the primary case study here. And then so machine learning, it's achieving this high human level performance on many tasks. And I'm showing you a few examples here. Recognizing objects and faces, solving captchas and breaking the security of those systems, and even beating doctors at various image recognition tasks, right? So all of this is well and good, but only if there are good people in the world, right? Now we know that this is categorically untrue, right? And that's kind of where security research comes in, right? And so one primary example of how machine learning fails, and this is an area where our group is very active in, is this adversarial examples, right? And so I kind of have this pictorial representation here, right? So I have this image here on the left, where your computer vision model thinks it's a cat. It turns out that there are specific algorithms that will allow an adversary to compute this thing here. This is some kind of very specialized kind of noise, so that when you add it to this base image here of this cat, to you as a human being, this still looks like a cat, right? At least I hope to all of us here, it still looks like a cat. But to the computer vision model now, all of a sudden it is extremely confident. This is an image of guacamole, right? And so this is just one example of the fundamental ways in which machine learning can fail when we use when we think of it from an adversarial perspective. Now, it's not only on images, right? So adversarial examples are kind of present everywhere. And so on this slide, I'm showing you a few examples. Malware detection, for instance, right? So we have models that will, take a binary, analyze that binary and say, is this malware or not malware? Turns out that an attacker can add or remove, certain few strategic instructions without drastically changing the operation of the malware, and it can completely trick these malware detectors and kind of get that malware downloaded onto your computer and executed or something like that. Right? Spam and phishing detection, another area people use machine learning models there. If you choose certain strategic words to throw into your email, you can pretty trivially evade these detectors, and in many ways. Evading spam detection kind of has been kind of the precursor to all of these attacks we are talking about today in images and voice and all of that, right? And so we have attacks in the voice domain. I can add certain kinds of inconspicuous background noise to a voice command and completely change its interpretation, and so on and so forth. There are adversarial examples in all kinds of machine learning tasks. So now one area our group is kind of focused on is what is the impact of all of this stuff when you use machine learning in some real physical system, right? Because that's kind of what computers are evolving to become, right? How much of the machine learning in these systems, how much do they understand and understand about what they are seeing? Right, and we know that even though the neural networks are very deep, the understanding is kind of shallow, right? And so we have several examples here. This crash with these Uber cars. This example of researchers who just project the kind of a planar, kind of a flat 2D image of a human being onto the road, and this Tesla or Mobileye system kind of detects it as a pedestrian. And to our own work that we did some time ago, where we showed how you can throw a bunch of stickers on a stop sign and have these models be kind of broken and start outputting misclassifications, right? And so this is kind of something I led a few years ago at this point, and the goal was to figure out an algorithm that will compute a set of stickers. You throw these stickers on an object of some sort. In this case, it's a stop sign. And then the machine learning model outputs, whatever the attacker desires. So, for example, make it a speed limit 45, or, pedestrian, project something onto a pedestrian and they are no longer classified as a pedestrian, stuff like that. One interesting thing I want to mention here is that the actual artifacts we used from our experiments, they are actually right now on display at the Science Museum in London. So that's if you join Wisconsin, no one can promise that, but maybe you have a shot of achieving wide impact like that, because that's kind of the work we like to do. Okay, so here is kind of a big example. An example of this attack. On the left-hand side, there is this stop sign with a bunch of stickers. There is on the right-hand side, there's just the regular stop sign, and at the bottom, the captioning kind of gives you the output of the classifier of the vision classifier. Okay, and so this is just a quick example, and this is a very big area of work for us. And so here is another project where we kind of go further down that line of just investigating what does it mean to attack these machine learning models. And so here we actually exploit the differences between how machines and computers see, right? between how machines and humans see. And so we are able to create these invisible attacks where an attacker can simply manipulate the light falling on objects. And then, the resulting image, humans just see the object is illuminated, but, due to certain specifics of how cameras work, there are these patterns injected in the image that kind of cause these misclassifications to occur. Okay. So, kind of taking a step back here, our goal is to, we kind of take this perspective of, how can it be broken so that we can actually make it safe and secure, right? So, I mean, although we do spend a lot of time breaking systems, our ultimate goal is to try and make these things secure. And the reason for that is a very fundamental one. And it's, in order to design defenses, you need to be able to think like an attacker. So that you know where to focus your defenses, and that's kind of the primary driving goal and mentality in our group. So trustworthy machine learning, one area, but our group, we have 4 primary faculty and several affiliated faculty, and so we look at many areas in computer security, including data privacy, user authentication, applied cryptography, human factors, all of these topics. Okay. So in terms of defenses, definitely, we are very interested in these physical attacks and how to defend against them, particularly how to use different kinds of sensing modalities and integrate that information, securely so that we can, with higher confidence recognize various, objects on the road in the context of self-driving, for instance. We are also interested in building systems that are privacy preserving. So a lot of these, automation systems, if I'm away from the home, then lock that door. All of these automations involve sensitive information that passes through these cloud services, right? So these cloud services are very large-scale systems, millions of users, all of their data in the same location. And the one thing we know from cloud services is that, they get hacked. They suffer all kinds of breaches. And so the question, we were trying to address here was, if you assume the attacker has already compromised these automation services that run in the cloud, what kind of guarantees could one provide? And in this project, we show how we can actually compute on encrypted data to enable this kind of functionality without leaking any of the sensitive information to a powerful adversary who actually has control of this cloud stack, right? So whatever the cloud stack is, the adversary is there, but because of our applied cryptography techniques, they're not able to recover what kind of sensitive information goes in these rules. So for example, this would be the location value here. On the privacy front, we are looking at various angles. So for example, our homes are filled with these voice assistants, right? And there's been many reports in the news of how these are falsely triggered, and this can actually lead to all kinds of spying and privacy invasions. We have projects that kind of looking at how to redesign these assistants or have bolt-on solutions that increase your privacy. We have work looking at how we can do private machine learning, on health records or other kinds of sensitive data. What are the privacy issues that come when you try to create machine learning models on sensitive data? What are the techniques? What are the foundational techniques one might use, so that these privacy issues do not exist? And finally, we're also interested in how the GDPR is changing the privacy landscape. One of our faculty members, Qasim, he's doing a lot of work on kind of automatically analyzing these privacy policies and actually translating them into actionable things one can do to better improve their privacy. We are also interested in authentication systems. So for example, we all hate passwords, and we often might create typos when we are typing in our password. And so one of our faculty members, Rahul, he is interested in studying how, say that you make a typo, can we tolerate those typos while still being secure, right? So you kind of capitalize some character or you do not capitalize it. is this scheme still secure or is it not? How do we go about reasoning through this kind of problem? So that's definitely one thing he is doing a lot. Okay, and so the final thing, in terms of the research results, is that we also have a team looking at how, all of this technology around us can lead to various nefarious uses. So in this case, we are looking at intimate partner violence and how, these smartphone apps and these IoT devices can be used by, by perpetrators to kind of, inflict IPV, on victims, right? And so, Rahul is one of the few people in the country who are doing this kind of pursuing these kinds of socio-technical solutions to study the problem, its prevalence, and what kind of defenses we can apply, what kind of socio-technical defenses we can apply, to counter this, this big problem here. Okay, so here is kind of an overview of the group. So we have 4 core faculty. And then we have several affiliated researchers interested in many, associated areas in computer security. And, we are all very happy to chat with you one-on-one during the later meetings, to chat about research. In terms of courses, we have a few. Ranging from cryptography, introduction to cryptography, right up to the latest topics in modern computer security. So there's definitely a breadth of courses, and this is in addition to special topics that each faculty member teaches that is kind of very tailored to their specific research areas within computer security. Okay, so I'll end there. We have an open house where you can meet all of our students. So I think this is on the website, and there are links to this on the website, on the Welcome Weekend website. So definitely check that out. We are all very excited to meet with you and discuss potential research. Thank you.
Thanks, Arlens. We're going to have like a brief break for about 15 minutes, and then we'll resume the talks. If anyone has any interest in, just taking a break, getting some water, whatever, this is the time to do it, and we'll resume the talks in 15 minutes. Okay, next up in the faculty talks this morning, we have the machine learning group, which we know is very popular these days. And we have 2 new faculty members, Sharon Lee and Fred Sala, who will introduce us to some of the exciting work and research that's being done by machine learning people here at Madison.
Thanks, Angela, for the intro. Very excited to see all of you here. My name is Sharon, and I'm assistant professor here working on deep learning. And this is a joint presentation with my colleague Fred, who's also here today. And so I would like to first extend a warm welcome so far. And because you can't visit Madison in person, and I thought this picture might worth 1,000 words to describe what Madison is like. So these 2 photos are of Lake Mendota, the bigger lake, if you look at the map. Hopefully will give you some idea of what Madison is like. And so I took the first photo when we moved here from California in summer 2020. And then the second one down the bottom was taken in fall when the leaves are changing colors. And so I have to say it's a really, really lovely place to live. And in case you're wondering about what winter is like, it's actually right outside of my window. And when it's not snowing, it's been pretty sunny most of the days. And so let me tell you a little bit more about the AI research here. So AI research at UW-Madison can be broadly organized into 4 subgroups. And this talk will be primarily on machine learning. We'll also talk a little bit about biomedical informatics towards the end. And we do have 2 dedicated talks, one on robotics, which will be given by my colleague Bilge at 10:30. And there's another one on computer vision given by Mohit at 12. So please make sure to check those out if you're interested on those research areas. And so here, I want to say that a large group of faculty members at UW-Madison are doing research in AI and machine learning. And this picture covers very broadly of faculty members from our CS department and also, in statistics and ECE department and so on. And so machine learning at UW-Madison is this active and growing community that brings together people, research, and courses from across the campus, focusing on both theory and application of machine learning. And so, as I mentioned earlier, faculties in multiple department and degree programs are affiliated with this group. And in case you haven't seen this, I highly encourage that you check out this website, machinelearning.wisc.edu. And this website has recently been redesigned, so it looks quite nice, I would say. So, and if you decide to join, you'll have the opportunity of hanging out and participating in this weekly Silo seminar, where we will be inviting external and internal speakers to speak on their cool ML research. And you can find many of our faculty's research talk in the past on this website, silo.wisc.edu. And so here are faculty members from the CS department who works more on the fundamental side of machine learning research. And I'm sure the reason that you're here today because you're intrigued by some of the faculty's research. So now let me give you some overview. I'll first talk about Jerry's research. And so most of you have already probably heard of adversarial machine learning from one of the previous security talk. And so an adversary can force machine learning model to make mistakes by making the small changes on the input. And so Jerry's group has done some really interesting work on theoretically understanding why this happens and how to defend against it. And in particular, he has done work in this sequential decision-making domain, such as reinforcement learning and multi-armed bandits. And so his research ranges from test time attacks, training time data poisoning attacks, and other subtle forms of adversarial attacks. And besides trustworthy AI, another interesting paradigm he's working on is called machine teaching, which is a really cool concept and can be viewed as the inverse problem of machine learning, where the goal is to design a training data for a particular target model, right? So if you think about machine learning, it's really the opposite. And so machine teaching has some really interesting applications in education and cognitive psychology, and also in computer security. And so if you're interested, make sure sign up for one-on-one with Jerry. And we have another faculty member, Ming Liu, who works on the theoretical side of deep learning and machine learning. And so his research interests are in analyzing and analyzing deep networks, where he tries to understand theoretically under what conditions the network can be trained and obtain good performance that generalize. And another line of his research is on robust machine learning, where the goal is to derive provable guarantees when those test inputs are different from the training data, such as being adversarially perturbed. And so this figure at the bottom shows you, after this attack, the important features shown by this red saliency map can change a lot, right? So with Ming Liu's research, he designs mechanisms to make sure that even with the attack, the model can still, capture this right or the correct region of the saliency map, which is cool. And so next, I would like to talk about some of the research that I do here at Madison. And I would like to motivate using this example at the bottom. And so imagine yourself, right, trying to develop a perception model of a self-driving car. And to do so, you collect some training data, perhaps based on the videos collected in urban driving scenes. And when you deploy this model in practice, that's when some of the serious issues could happen. Because the classic machine learning assumption that we've learned from the textbook is that the training and test data distributions often match each other, sample to IID. However, this rarely holds true in some of the real world problems. And so, for example, on the right side, this is a realistic scene that the car can run into, right? Those are the rocks on the mountain road. And we call this out of distribution because the model was never exposed to such categories during training time. And so this brought us to this fundamentally important problem, which is how can we build machine learning models that can function reliably in such an open world, right? So the goal of my lab is to build algorithms towards reliable open world machine learning that can function safely and adaptively in the presence of evolving and unpredictable data stream. And an important problem towards this goal is called out of distribution detection, which has been gaining a lot of research interest these days. And so our lab has made some quite exciting progress in the past, really pushing the state of art in terms of algorithm design, theoretical understanding, and also making the algorithms applicable and useful in the real world. So it's a really exciting space to be in, a lot of work to be done still. And with that, I would like to transfer over to Fred to continue the rest of the presentation. Fred, you're in charge now.
Thanks, Sharon, and appreciate the introduction. Hi, folks. So I'm Fred Sala. I'm gonna do the rest of these slides, and I'll start by talking a little bit about my research. So I'm especially interested in the limits of machine learning. So far you've heard about some of the really awesome stuff that we can do with machine learning models. A lot of my interests are when we can't do things with machine learning models instead. So I'm especially interested in how far we can take modern machine learning models. They're no longer just used for fun tasks like detecting your relatives on your Facebook photos. They're actually making some really important decisions about the real world now. So things like who should get a loan at the bank, when we should have someone undergo surgery or applications like that in medicine, when we should evacuate people because there's a disaster or not. And as Sharon mentioned, of course, as we're going towards self-driving, then the decisions are really important because choosing to brake or not to brake is a real life and death situation pretty often. So given all of these really important applications of machine learning in some pretty critical situations, I think it's really important to understand the guarantees that we can provide for these systems. Basically, in what situation they'll work and in what situation they won't work. I'm especially interested also in the principles that tend to govern this kind of behavior. So when we sort of pull back the hood and look underneath, even though a lot of these models look like black boxes, my research tries to understand what are the key principles that actually make things work or not work. So there's a couple of cool applications that I enjoy working on in here. So one of the really interesting things about machine learning models is that even though you approach them from the point of view of algebra, optimization, statistics, pretty much all of them have this really interesting implicit geometry that often says how well they work or don't work. So when we do things like try to provide representations of data that has some graph structure, has relationships between them, it turns out that this geometry really tells us how well things work or don't work. So Sharon, if you click that button over there, that's an example of deep learning, just learning how to position points in a network. And using a certain special kind of geometry is actually really important here. Another really interesting aspect of trying to understand these limits is dealing with less supervision. So most machine learning models tend to be extremely data hungry, and it's really important to find a way to cheapen how we access this kind of data. So a lot of really awesome research lately involves using more efficient methods. But unfortunately, this also means that things are noisier and there's a bunch of trade-offs that we have to better understand. And my research tries to pull out those trade-offs. And finally, I'm also generally interested in theoretical insights for any kind of systems that are built from data, so machine learning or otherwise. And I think this is a really important space. I think a lot of theoretical results are now in a position to guide users of machine learning, especially for these high stakes applications. Okay, I'll also talk about Josiah's research. So Josiah is an assistant professor who's joining us this fall. His goals are to develop general autonomous agents. So these agents include things like software, but also awesome things like robots. And all of them try to accomplish goals by taking actions and then receiving feedback from those actions. So this is what's called the reinforcement learning framework. So for this goal, Josiah's research is to build general purpose RL algorithms, and they have to scale to large situations for real world challenges. So to do this, Josiah works on improving data efficiency, because these are also extremely data hungry models. He tries to create multitask reinforcement learning models because he wants to handle many different situations concurrently. And he also works on technical problems like learning hierarchies, abstractions, representations for reinforcement learning. His research is both theoretical and also empirical in both these areas. He also is very interested in applying this to multi-agent systems, autonomous agents, and also robotics. So if you're interested, you should get in touch with Josiah. This is really exciting work in reinforcement learning. Finally, I also want to talk a tiny bit in the couple of minutes we have left about some of our collaborations. So we work a lot in interdisciplinary areas, and we frequently collaborate with Ece, so the Electrical and Computer Engineering Department, Biostatistics, and also the Math and Statistics Department. And just very quickly, I want to bring up a little bit of the research that our Ece collaborators do. So for example, Dimitris works on fast and robust distributed training for machine learning models. So he tries to figure out how you can split up optimization into parts in order to make them more efficient, how to deal with challenges to robustness, like these parts going offline or having issues, and how to make all kinds of different machine learning problems more robust. So for example, for robust perception. So his research is at the meeting point between optimization, systems, theoretical analysis. Also, Rob Nowak is currently working on active machine learning, which is a really exciting area that allows humans to get inside the loop to help improve the training of machine learning algorithms, rather than just going through the process of building large data sets and running them through and training models. And just very briefly, I'll talk a little bit about some of our biomedical informatics collaborators. And this is one of the most exciting areas for applying machine learning ideas to. So Tony Gitter works a lot on algorithms that try to leverage biological networks to try to connect different kinds of experimental data, and especially to figure out relationships between them that are difficult to detect otherwise. So this is applied to a lot of different areas, but most excitingly, it's really useful for understanding and detecting diseases. Sushmita works a lot on developing computational methods to handle genetic areas, which become these very high, large-scale, challenging computational problems. And basically, they get at understanding the fundamentals of how cellular networks actually function. And finally, Colin's work is on trying to understand genomics, especially. So figuring out how organisms evolved at the molecular level. And this turns out to involve one of these extremely difficult computer science problems, which is sequence alignment. And combinatorial optimization and machine learning are both involved here to try to figure out how to analyze these huge DNA chains that basically tell us which organisms are related to each other. And last but not least, Mark Craven is interested in a whole bunch of different machine learning methods to infer models of biological entities. So things like interactions between genes, proteins, clinical environment factors, and also phenotypes. And all of these models are used to reason about these entities. So I hope you've enjoyed this overall description of all the different research areas that are touched on by AI and machine learning. I hope you enjoy the rest of the visit. Thanks so much for coming to our weekend, and I hope you'll get a chance to come and meet with us in the one-on-one talks. We'd like to chat more with you.
Look forward to speaking with some of you during the one-on-one. Thanks, Fred. That's great.
Thank you, Fred and Sharon. And our next speaker will be Professor Paul Barford, who represents the networking group.
All right, thanks, Angela. Hello, everyone. Hope you can see my screen. I'm going to put it into presentation mode. And wow, that was a great presentation by Fred and Sharon. You know the old saying, never follow animals or children on stage. I think they need to extend that to say never follow animals, children, or machine learning professors in a talk. In any case, my name is Paul Barford. I'm a professor who studies computer networking, and it's a pleasure to be able to present some of my work and some of the work of my colleagues in our group today. Okay, so this is the computer networking group. Professor Shuman Banerjee, myself, and our new colleague, Ming Liu, who's actually going to be joining the department in the fall. We study diverse areas, and in the course of the next 15 minutes, I'm going to give you thumbnails of those. What I hope is that some of the things that I talk about inspire you to get in touch with any one of the three of us. We all have office hours later today, and then there is a networking group session from 5 p.m. to 6 p.m. Central Time, which you can join, and we'll have sort of open conversation then. So probably most of you are familiar with the general aspects of networking research, and we touch on them pretty broadly in our group. Of course, in the scope of networking research, the internet is a prominent presence, connecting an ever-growing number of systems and devices and people across the world. An important additional aspect is the connectivity that we enjoy wirelessly that allows us mobility and to connect all sorts of devices that would otherwise be impossible to connect by wires. Over the last 10 years, many of the concepts that grew out of the internet and wireless connectivity have migrated into the gigantic data centers that power many of the services that we enjoy on a day-to-day basis. And of course, those data centers wind up being the sources of much of the traffic that traverses the internet today. And considering the scope of sort of these three areas, if this is a sort of a high-level taxonomy of networking issues, what winds up happening from a research perspective is that we touch many other domains that are related to, but slightly outside of networking, namely security and privacy, algorithms, machine learning, big data, and so forth. So even though computer networking has been an active area of research for decades, there are many big opportunities going forward, and we're looking for smart and hardworking people to help us solve these problems. One of the biggest transitions over the last 10 years recognizes that we no longer have to rely on special purpose hardware that's developed by major companies and has largely been closed to research and to even operators in terms of what those systems can do and how they can be used. And the idea of cracking open those systems to software and programming is an area that's been very active for the last decade and continues to offer significant opportunities. The idea of programmability in networks has evolved into something that considers the possibility of actually creating virtualized capability that can be chained together to offer new types of services and capabilities. This is network function virtualization. Shifting into the wireless domain, there are virtually endless possibilities there when you consider what the challenges are in terms of managing spectrum, in terms of range, in terms of quality, in terms of bandwidth, and the questions abound in terms of how we can continue to enjoy higher and higher bandwidths without the need for tethering to some kind of fiber or copper connectivity. And then as we proceed, and I'm sure you're all aware, more and more devices, and including vehicles, are becoming connected to the internet. And every time a new technology evolves that requires connectivity to the internet, a host of questions emerge that need to be answered in terms of how those are actually connected, how they're managed, and we're looking forward to addressing those as we proceed. So shifting now into some of the work that my group has done over the years and continues to focus on, one of the major issues that we've considered and that is always sort of omnipresent in computer networking is how we can improve performance. And it's not just the issue of performance, of course, because performance without resilience is not necessarily that useful. And I think the best way to sort of define the scope of the work that we do in my lab, the Wisconsin Advanced Internet Lab, is really by the approach and the techniques that we apply, which tend to be very empirical and experimental. So a lot of our work revolves around developing techniques and tools for gathering data from the internet. We apply a wide variety of analytic techniques to extract information from that data. And then we utilize the insights that we're able to gain from the analyses to be able to build and test new systems and protocols that can improve performance and resilience and develop new services in the internet. Okay, so one of the recent projects that we've worked on has a very sort of societal focus, which is assessing internet risks from the perspective of climate change, something that I'm sure that you've all heard a lot about over the years. My wife happens to be a climate scientist here on campus, so this is something that I live with every day. And in the last couple of years, just to give you a little bit of a flavor for this, we've done some work that just asked two simple questions. One question is, given the effects of coastal sea level rise due to the warming climate, what is the potential impact on buried cables? So one of our projects over the years, Internet Atlas, has focused on creating maps of internet connectivity throughout the US and the world. And what we did for this project was simply to say how much of these buried cables are going to be underwater in the next 100 years. And what we found is, unfortunately, an awful lot of the internet that's in coastal areas is actually going to be underwater. And while at first glance you might think, well, you know, what's the problem? I mean, internet conduit must be resilient to water. The answer is yes. In general, it's water resistant. But none of the buried cable in the coastal areas was meant to actually live underwater. And simple questions like how do you service buried cable when it's underwater become significant. In any case, that's one study. A second study that we finished last year examined the risk of cell tower infrastructure to wildfires. Of course, you've heard a lot about wildfires over the last couple of years and their rising prevalence because of climate change. And what we found is that indeed a great deal of cellular infrastructure is under threat due to wildfires. We focused principally in the United States. And what we were able to do is to assess and project what areas are under particular threat and then how those areas should be hardened or otherwise considered to reduce that risk. And fortunately, our studies have received a lot of attention in the popular press. So you can go online and do a Google search in Google News and find that that a lot of these studies have been picked up and publicized, which is fun. All right, I need to move along quickly here. Another project that we've worked on recently is a little non-obvious, which is how to use the internet to sense vibrations. So ground motion and structural monitoring is critical for many public safety reasons. And what we're investigating is what I'll call opportunistic vibration measurement from computing and communication infrastructure. And the observation is that if indeed ground motion and vibration can be detected by deployed internet, buried conduits and so forth, then we could potentially have a national capability to monitor for vibrations that would otherwise cost a huge amount of money and be very difficult to deploy using standard tools and techniques like seismometers. And what we found is that indeed internet cable and fiber is sensitive to vibration and portends, or our hypothesis with respect to vibration sensing is supported. So that's an exciting opportunity that we continue to pursue. Furthermore, I don't know if anybody has ever seen the YouTube videos of the guy shouting at disks and watching the read-write latency grow as he shouts at the disks in the data center. You can find that on YouTube. But what it suggests is that hard disks themselves might be sensitive to vibration and might be able to be used for vibration monitoring. So this is a study that we're in the process of pursuing. All right, so we've got other projects related to internet measurement and analysis. I need to move quickly here, so I'm going to just step forward. Professor Banerjee, as I mentioned, is our expert on wireless and mobility. He set up significant infrastructure in the building and on campus to be able to conduct empirical research. So we operate our own 4G network on campus. We own TV white space. We have a huge deployment of 802.11 base stations that are instrumented for experiments. And indeed, Professor Banerjee has even deployed significant infrastructure on buses that carry people between Madison and Chicago, and has done a lot of work on experiments on that relate to connectivity on those buses. So that infrastructure and the work that he's done is really quite impressive. In more recent research, he's deployed capability related to mobile sensing and edge computing that enables tracking of automobiles as they drive down roads. So it enables basic questions to be asked about driving characteristics, and some of this work is really quite interesting in terms of the data that they gather and what they can extract from it. It includes aspects of speed and direction that you wouldn't think would otherwise be able to be extracted from simple measurements of connectivity to and from the moving vehicle. Okay, I'm going to move quickly here through Professor Banerjee's stuff because I want to get to Professor Liu's stuff, and I've only got 2 minutes left. So as I mentioned, Ming Liu is going to be joining us in the fall. We're thrilled to have him join the networking group. His research is focused particularly on programmability in smart devices. So his approach has been to build systems in emerging programmable hardware, in particular programmable network interface cards. And his first project that he's focused on currently is on network interfaces to storage systems. So he's looking at things like bunches of flash devices and how those flash devices can be effectively connected through smart network devices. 2 other projects that he's working on relate to programmable network virtualization, again, rethinking the role of smart NICs and programmable switches, and how software and programmability plays a role in those devices and their deployments. And then thinking more broadly in terms of backbone connectivity, how functionalities in data centers and in backbones can be reconsidered with significant programmability in those locations. So that concludes my talk. We've done a lot of good work, and it's reflected in some of our accomplishments. We're looking for great students to join our groups so that we can continue this research. Thank you very much for your attention, and I hope you enjoy the rest of the time here in the virtual welcome weekend.
Thank you, Paul. Next up, we have Ferris Kutrice from the databases group.
Hello, let me actually try to.
Share your screen. There it goes. Thanks.
Let me make sure that I can start the presentation. Okay. Okay, great. Can you all see that? Okay, great. Hello, everyone. My name is Kutrice. I'm an assistant professor at the database group here at UW-Madison, and I'm really excited to talk to you a bit about what the group is doing. Okay, so let's get started. So data is everywhere. We use data to do business intelligence, to have scientific discoveries. Online platforms use data to make decisions. So data is everywhere. And in general, when we are talking about data, we are talking about the data pipeline. So this data pipeline takes data in a raw format. You can imagine data as text, or data as images, or it's a table or a web page, and then this data has to be prepared in some way, right, and then stored. So these preparations means we have to extract, we have to clean, we have to integrate different data sources, we perhaps need to augment our data, and then we store it, and after that we do the processing. And here by processing, we may mean the traditional data analytics, so for example, SQL queries or other traditional database tasks, or even more recent things, for example, creating ML models, creating interesting visualizations, for example, figures that you may want to get insights and so on. So we are kind of interested as a group, and I'm going to talk in a bit more details later, in the whole pipeline going from the raw data to the actual insights that we get in the end. And we are kind of involved in every step of this overall process. Okay, and here, I mean, this is a slide that I always like to show, and every year it changes. And it's fine if you can't see all the details, but this is actually all the companies and the industry that is involved with everything that has to do with this data pipeline. So here you can see things from very basic infrastructure like AWS, Microsoft Azure, to everything that goes up to applications and so on. So the point of this slide is to show you that there is a huge interest in this data pipeline, how to make it faster, how do we make it to give us better insights, and so on. Okay, so what are the challenges now? So the challenges first is, as we said, how do we prepare, how do we organize, and how do we store data? And then how do we make this pipeline go faster, right? So this is kind of the stuff we are interested in answering, right? And both of these questions will lead to will have a major effect in how fast we can get from data to insights, and how efficiently also, right? Because we don't want it only to do it fast, but we also want to be able to get better insights about how to use our data in daily life or as part of a business and so on. So this is kind of the main questions that the database group is looking at. It is a pretty old group. It was established in 1976, so that was 10 years before I was born. It has been very influential. So our students have been professors and researchers at top universities and research labs. So if you go to Microsoft or Google, you'll find UW-Madison graduates from the database group everywhere. And they have also been leaders behind major products in databases in industry. So the database group has been very, very influential, both in academia and both in industry. So this is who we are. So Professor Haidon, me, Professor Jignesh Patel, and Professor Xiang Yayu, who is the most recent member, joined a couple of years ago. And what I want to talk about briefly next is just go over a few of the projects that we are working on. I won't go into detail about everything we are working on because it's a lot of stuff, but I want to just give you a taste about some of the things we are working on. So as we said, the kind of main thing we are trying to do as a group is go from data to insights. So some of the particular areas we'll be working on is bare metal execution. So this means if we have a data processing task, can we make it run as fast as possible in the hardware that we have, right? So that's what we call bare metal. So can we try to create an algorithm that's going to run as fast as possible? We're also interested in end-to-end systems. So how we can build this system that go from the raw data to the insights, but like as a fully fledged systems and not individual parts. We're interested in data preparation. So how do we actually can take this raw data and then prepare it in a nice format that they can then use to a machine learning pipeline. We're interested in the theory, in the foundations, and then we're interested in how we can co-design using both software and hardware. And now let me give you go into a bit of these things in a bit more detail. So the first thing I'm going to talk about is data cleaning. So what is the problem of data cleaning? Well, you would expect that the data that we're dealing with is nice, but it's often not nice, right? So it's often dirty and contains errors. So here you can see two different tables that have information about people. And here you can see, for example, if you look at X1 and Y1, you can see that it's basically the same person, but the information about this person is written in a slightly different way, right? So you have Dave Smith or David D. Smith in the other one, and then the phone number includes the area code in the one table, but in the other table it doesn't. And then you can see that maybe there's also some other inconsistencies. For example, for Dan Smith, in one table the city is Middleton and the other is Madison, right? So you could expect that this could be an error because the cities are neighboring, and some way of extracting our data showed Middleton and some other way of extracting the data showed Madison. And then in the second table, you can see, so this is one type of errors that we can have and this particularly appears when you have data integration. The other type of errors is that we may have missing data, right? So here you can see the second row and see that the population is written as a string, but in the other rows it's written as an integer. The density is not known, right? So it's kind of an empty field there. So the whole question is how do we deal with this data, right? Because this data is going to be forwarded to through the data pipeline to some downstream task that's going to do some processing. So we need to make sure that it looks good. So a basic problem, and this is what Professor Anhaidon is working on, is the problem of entity matching. And this says, well, given tables that refer to different entities, can we actually find the entities that are the same but are perhaps described in a different way, right? So can we match tuples, records that correspond to the same physical entity, right? So here, for example, we want to match X1 with Y1 and X3 with Y2. Okay, so this is a problem called entity matching. It's a really hard problem. People have been working for a while, and what Professor Doan is doing is essentially created Magellan, which is an end-to-end system for entity matching. So it's basically a collection of different functions and libraries that allow someone to build a system to do this entity matching. And this actually led to a startup, Green Bay Technologies, that was kind of recently acquired. And you'll see the theme also when we talk about Professor Zignesi's work, that a lot of our work in the group is very applicable, and it also leads to startups and impact in the industry. So the second project that I'll talk about is a project that Professor Jignesh Patel is leading, and this is how do we create conversational interfaces for essentially data scientists, right? So what we want to do usually when you are a data scientist and you want to do some data processing, what you do is, you write your scripts, and then the scripts could use different languages, different libraries, and you have to connect them and so on. And then, if you make an error, then you have to go back and fix it, and that could be really hard. So the whole idea is, okay, can we have a system that's going to basically improve that so that we can more easily go from again, data to insights. So you can see here kind of how it would look like, conversational output that you would say, okay, the Ava, which is the bot, says, what do you want to do next? And you say, some an ROC plot, and they say the plot is generated, and then there's a dialogue, and then you tell the system what it wants to do. So this prototype is now again another startup called DataChat. It's been doing really well. Okay, so let's go to kind of the next project. And this is kind of more on Professor Xiangyao's work. He's working on next generation database systems that have to co-design taking software and hardware into account, right? So the whole idea is, well, there is a lot of new technology, new hardware that's coming up. So for example, we have new processing units, we have multi-cores, we have GPUs that are extremely good, we have FPGAs, we have new types of memory like NVMs and SSDs. We have new network technology, smart NICs and RDMA technology. We have cloud architecture. So all this hardware exists there. So can we create systems that try to exploit this hardware, and so that, and we also design smarter software for this particular hardware, right? So this is what we call co-design, right? So can we actually look at this architecture and say, okay, this is how we need to build a system to take advantage of this architecture, right? So for example, to give you a concrete example, if you have a GPU available, you may ask, okay, what kind of data processing should I offload to my GPU? And if I do that, what are the trade-offs, right? So can I just do everything, or do I have to do a particular, let's say, database operator, and which database operators work best, and how do we decide how we're going to do that, what are the bottlenecks, and so on. So there are very interesting questions, and many different projects in this area. And for the last part, I'm going to talk a bit about what I'm doing. So one of the projects that I'm really excited about is, and this actually has to do with also Professor Xiangyao's work, is how do we do data processing that is topology aware? And the idea is that if you have a cluster, that this cluster could be in the cloud, or it could be in your single machine, then your computing nodes are connected in a bunch of different ways, right? They could be in a tree, they could be in a grid, they could be in a fat tree. So the idea is, again, as we said, with co-design of software and hardware, can you design faster algorithms by basically looking at the topology and exploiting this topology, right? Instead of creating an algorithm that's oblivious of how things are connected. The second thing I'm interested in is data markets, right? So data markets, what they're doing is basically they're looking at the fact that data is a commodity, that it's sold and bought in the web. So for example, you have a data market, you have a seller, the seller has some data, and then a buyer will come, will ask a query, and then we basically want to give the query and then give some price, right? So now the questions we can ask in this framework is, okay, how do we make this work? What are the limitations? How do we do this pricing so the users cannot cheat and they get the information that they want? So this is kind of a project that we had a few years ago that's called Kirana. And then some more recent stuff that we are dealing with is, okay, if we're not selling queries, but we are selling models, right? ML models, well, how do we price these models, right? So how we can capture the value of what the model is doing, and what are the trade-offs between accuracy and price. I think I'll stop here. Again, this is kind of like, again, some of the stuff we're doing, foundations of data management, co-design of hardware and software, data cleaning, data integration, data preparation, and then data science and big data. Please visit our group website for more information. And we'd be very happy if you come to meet with the database group today, 6 to 7. We have an open house, so please come. Students will be there. You can ask them questions about any of these projects and some of the other projects that I didn't get a chance to talk about. So I hope you have a very nice rest of the visit day. And yeah, please let me know if you have any questions about any of these things. Thank you so much.
Thank you, Ferris. Next up is Professor Bilge Mutlu, who is representing the robotics group.
Hello, everyone. Do I sound okay? Angela, I do?
You sound good, and I can see your slide.
Great. Hi, everyone. It's good to be speaking to you, and I look forward to meeting you one-on-one. So I'll be talking about the robotics group. You know, my own work sits between robotics and HCI. You might see some of my work in the HCI group's presentation, but I'm going to be representing primarily robotics today. So the robotics, I think to start a discussion of robotics, it would be good to define what robotics is, right? So a definition that you might find on the web is that as a field of computer science and engineering, it's concerned with creating robots. And these are devices that can move and react to sensory inputs. Now, this is an incomplete definition, and there aren't that many good definitions out there, but I'd like to highlight movement, right? A robot moves in the physical world. It senses the physical world. And then the third part that's not here is that it makes decisions about the physical world, about its actions, about what it's recognizing. Okay, there are three components: movement and actuation, sensing, and decision making. So, like I said, I'm representing robotics group, and not just for the computer science department. So in the computer science department, with 4 of us do robotics related work. It's myself, Mike Gleicher, Josiah Hanna, and Mohit Gupta. In addition to that, we have a larger robotics group on campus from engineering. We have 2 colleagues from mechanical engineering, Peter Adamczyk and Michael Zinn, and then also one from industrial engineering, Rob Radwin. And there's kind of a network of and kind of a complex grid of how all of us collaborate across different projects. I'll be kind of sampling from work primarily that I'm involved in because I know those more, but I'll kind of give you a sense of what everyone's doing. So when we think about robots, I would recommend thinking about them as kind of different platforms, and I'll be talking about 2 platforms today. One is physical robots. These are robots that can do physical tasks and can collaborate with people. They can work on their own, but really acting on the physical world to do tasks that we want them to do. The second type of robots are social robots. If you have for example, a Google Home device, think about that, but think about it having more physical capabilities, right? It sits in your environment, maybe it moves in your environment, maybe it follows you, maybe it looks at you, right? So, but its interaction is primarily in the social domain. So the examples that I want to give are going to go sample through these different platforms. The first one is work on collaborative robots, the physical robots, and this is joint work between myself and Professor Gleicher. Here we were really interested in building very natural ways of controlling these robots. Okay, imagine that you want to control this robot and you can just move your arm to show to the robot the motion that you want it to do, and the robot follows that, right? That's sort of the naturalness that we're trying to get to. And so, you know, getting to that is not that easy, right? We have to solve a lot of problems because the geometries of my arm and the geometries of a robot arm are actually very different. And every robot platform is different. And then we have to, you know, once we solve that mapping problem, then we have to solve other issues, like there might be artifacts that might come up, such as singularities and things like that. We need to also solve those problems. A few years ago, we addressed these problems and came up with a motion framework that allows us to do this kind of control. So what you see here is a user who's never interacted with a robot before, used a robot before, come in and immediately do something extremely complex, right? Playing with Tinker Toys. If you wanted to take the current existing interface for these robots and try to do this operation, it would take you about half a day to program this. But now we can do this in real time and also do more sophisticated things. So that's a co-located scenario, right? I can see where the robot is. I can see the task space. What happens if the robot is far away, remote? Maybe the robot is on the moon or the space station. In this case, we pair the robot with another robot and provide that other robot with a camera and task that robot to give the best view that it can give to an operator. Okay, we do this by putting both robots' control into the same optimization and solve for a certain set of heuristics and constraints. Here is the demo. What you see on the left is the operator's view. The operator is getting that camera view from that red robot, who's autonomously providing that view, and its job is to really give the best view. For example, if the first robot, the gray robot, is actually occluding the task, then the other robot will go around and get closer to it. If the task is small, for example, and it needs more focus, the robot will zoom in. If the task is big, it's making gross motions, then the robot's going to zoom out. So we build these heuristics into that real-time optimization, and the robot is really able to support the operator's task. Now, these are all nice, but as you can see that all the tasks are kind of picking and placing things. Those are very simple tasks. So how about tasks that are much more sophisticated, right? What would I do if I wanted to support a task like this? Imagine this person who's asked to build a recipe using ingredients from all these cups, and then mix them up and stir them and pour them and manipulate things that are much more complex, right? This is a complex manipulation task. It's not just picking and placing things. Okay. If I wanted to support this, what would I do? So we're able to support that level of complexity as well. What you see here is, again, a person who's never interacted with a robot or used a robot. We're carrying their emotions to a robot. This time we're dealing with both arms, but not just carrying of the motion to the arms, but also the coordination between the two arms, because if they're not coordinated, turns out that the robot can drop things, crash things, because there's a lot of drift in motion transmission. But using deep learning methods, we can actually create that coordination for multiple limbs. So now we are in the process of applying these ideas, this framework, into practical problems. We have a large project between myself and Professor Glacier, also from engineering, Mike Zinn and Rob Radwin, in collaboration with the Boeing company, to build robotic tools that can follow the same paradigm to build aircraft. Okay, imagine this worker who is placing something on the fuselage of an airplane. Now, instead of using that tool, controlling the robot that applies that tool, right? So here's a sort of ongoing work just to give you a glimpse of what that might look like. We built an augmented reality-based interface to task such a robot. If I wanted to do sort of repeated and varied tasks and wanted to tell the robot what it should be doing, this is how we're supporting it right now.
When facing a new task, instead of creating a fully autonomous robot behavior, the system we are developing allows workers to use augmented reality to annotate a video feed with the actions they want the robot to execute. Once a behavior is created, it can be run, checked and corrected if needed to ensure that the desired outcome is reached. This interaction is especially suited for tasks with high variability, where creating a fully autonomous robot behavior would be prohibitively expensive and complex.
So let's move on to the social robotics domain. Okay, if I have more of a social agent, how are we thinking about that? So the example that I'll give here is work between myself and a former Wisconsin student who's a professor at University of Illinois Chicago, and also sort of affiliated with us. We built a learning companion robot, an educational robot that will read with children. And the idea is that the robot is not reading to the children are reading to the robot, and the robot is really supporting reading-related activities. It's helping the child choose books to read, and then as the child is reading, set reading goals, and also connect what the child is reading to other things that the child read. So it's providing commentary and all that. One of the things that we want to do is to build these systems and see, put it out into the real world and see how people are actually using it, right? So what you see on the right is how the children are using it on the ground, on a couch. How are you actually using this technology? And then track over time what kind of use patterns we see, right? Are they reading? Are they actually finding it to be motivating, right? Compared to some other kind of activity. So now we're interested in longer term deployments. For example, this summer, we're going to do a summer-long deployment with a different robot platform and support reading activities that way. Thinking about social agents, one of the things that we're interested in is not just to build these systems as kind of static systems, but we want to build them as systems that learn and adapt over time, right? So here I want to talk about Professor Hanna's work, and he's particularly interested in reinforcement learning, right? So he wants to build robotic agents that learn and adapt over time, having certain goals and taking the right actions toward those goals, okay? And to really kind of utilize reinforcement learning to address challenging real-world tasks. And the place that he's applying this experimentally is robot soccer. He, in fact, has a lab with soccer-playing robots, and the idea is, each robot is responsible for making decisions about, okay, which way do I move? Should I go after the ball? Should my partner go after the ball? If I kick the ball this way versus that way, how do I actually achieve that? as a part of this problem is that, how you do reinforcement learning in a efficient way, right? Can we use small amounts of data to do machine learning? And can we do things in simulation, really learn new skills, how to take certain actions and transfer that to real robots, right? That's one of the things that they've been doing. And really use combine demonstrations from different agents, could be humans, could be other robots, and integrate that with reinforcement learning in order to perform complex tasks. And the last line of work that I'll talk about is building both interfaces and computational tools to program robots. How do we actually program these very complex robotic systems? Because when I talk to graduate students who are interested in robotics but haven't done robotics, they come to the lab for the first 6 months. They're just catching up with like, how do I actually program a robot? Where do I start? That's a lot of skill to build. How do I actually get someone to sit down and immediately start programming robots? Okay. The first tool that I'll talk about is a graphical programming environment. And as designers, the programmers are building a program using this graphical environment, we're using programming languages techniques to actually analyze the resulting program and find issues and problems that might arise in the interaction and address those problems. We can give the designer or the programmer feedback for them to fix it, or we can fix it in the background ourselves using synthesis methods. Okay, so this is one example. Another example is how about we don't even have any kind of interface? We want to just capture actual real world interactions and use that as a basis for a program, right? So let me show you a quick video on this work.
Synth is a design tool that facilitates the rapid prototyping of human-robot interaction programs. Synth records designers as they act out an interaction, and then synthesizes a full interaction from the designer's performances. Designers are equipped with microphones to capture speech and armbands to capture movement. Synth stores recorded speech and motion within an execution trace. Given a set of execution traces, Synth will synthesize a human-robot interaction program in which each execution trace is realizable within the program.
Right, so this is, why don't you act out the interaction? We'll learn from that. What if we support them using other types of interfaces? So next I'm going to talk about a tabletop interface. This time programmers or designers are not acting it out, but they're demonstrating it using a couple of figurines, right? One of the figurines represents a robot, the other one represents a user, and you can demonstrate how the interaction should play out in a particular space using these figurines. So this is my last video. Let's watch that.
We present Figaro, a tabletop tangible user interface for authoring human-robot interactions. Robots say, "Hey, how's it going? My name is Robot." Figaro is primarily controlled via a tablet interface, and before beginning the design, the user must draw out a rough outline of the physical layout that the robot will be placed in. Once the layout is loaded onto the tabletop, the human and robot figurines can interact with each other within the virtual environment. The figurines are affixed to wireless joystick bases, which give them more tangibility.
And one of the things I want to highlight is that when designers or programmers are expressing these programs with the figurines or acting out, whatever the resulting program is immediately automatically implemented in the robot and ready for testing, right? That's the kind of like, 0 to 60 kind of we're looking at, right? So really go from the idea to the program that you can simulate and test immediately. So I'll stop there, running out of time. If you want to learn more about this work, you can go to robotics.wisc.edu. This is our campus level website that will point to the various labs. I also know that a number of my students are going to be at the HCI open house this afternoon, 1 to 3 p.m. And I also look forward to talking to you one-on-one. I hope you enjoy the rest of your welcome weekend, and thanks for the opportunity.
Thank you, Bilge. Next up, we have Laura Stantone from the Programming Languages Group.
Can you hear me now?
Yes.
Yeah, good. Okay, sorry. Okay, hi everyone. Yes, it's always hard to, I feel like every year I have to give the talk after Bilge, and then everybody has seen videos of cool robots, and now I'm gonna tell you things that don't have videos of cool robots. So it's pretty hard to compete. but I hopefully can convince you that programming languages research is cool. So basically, the whole motivation behind doing research in programming languages is answering the following question: should programming be painful? So if you think the answer is yes, you shouldn't do research in programming languages. If you think the answer is no, maybe you should do research in programming language, because we're going to try to help people program and make programming easier for them. So why is programming painful? Well, since I argue that basically nowadays, more or less, whatever you're going to do in computer science, you're going to have to deal with some amount of programming. And this is kind of like, this picture shows what programming used to be. You just write code that does things and runs on your computer and sorting algorithms and whatnot. But programming is changing in a way that is affecting everything. So for example, even network infrastructures, data centers, nowadays they are configured using programs, and these programs can have bugs, and these bugs can be very costly. Like they can cause Google to go down, and then Google is sad. Similarly, people use these days programs to collect data, and then they use other programs to take the data they've collected and generate some fancy machine learning models. So even machine learning these days is basically programming. And unfortunately, now these programs are permeating in very interesting places. So programs are not only used anymore to do things like sorting a list or run a robot, they're also used to make decisions that have a high societal impact. And so here at Wisconsin, in the MedPL group, what we are trying to do, our mission is basically to build tools that help programmers write software that meets their intent. So our goal is basically to make sure that programmers write something that does the thing they want. So why do we, in what ways can software not do the things one wants? So for example, a software can have a bug, and a piece of software has a bug, and bugs are expensive. So this is actually an old study from 2013 that was showing that already back then, just debugging software, so just like figuring out what is wrong with your software and fixing it, was costing around $312 billion per year. And I think right now these numbers are probably 10x that. It's like there is so much more software. Before I mentioned that software is used in data center networks to basically run the data center, and things can go wrong here. And very often you read something like this: oh, somebody misconfigured a network device, and this led to an outage. And this one is from Microsoft, but you can find more or less one for every each of your favorite provider. There was some outage that was caused by some programmer doing the wrong thing. And as I mentioned before, now software is being used in unusual ways. So I'm sure many of you have seen this picture before. This was a study done by ProPublica 5 years ago at this point. So they had found that software is being used to make weird decisions, ones that have high societal impact. And one should argue first that maybe we shouldn't use software for these decisions, but that's a different discussion than the one we're going to have today. But what they observed here, the software was used to decide who will get out of prison, basically who will get parole after ending time in prison. And it turns out that this software was biased in a way that was affecting one racial group more than another. So this is really bad. Like software here, a bug, you can call this a kind of a bug in software, an unintended behavior, was that this was having high societal impact on an underrepresented group, or in general on a group of people. So this is a bad thing. We don't want this. So what should we do? As programming languages researchers, we have an army of them here. We basically, our goal is to basically make sure that these things don't happen and to help people write good software. And we have a nice group of faculty here at Wisconsin. And in fact, we are pretty good at programming languages, it turns out. So this is every time somebody shows you a ranking, I'm always going to show you the ranking where we look best. And so there is this ranking called csrankings.org, where you can go and select whatever fields you want. And of course, I selected the ones we care about, which are programming languages and logic, which are the two things we work in the MedPL group. And if you select those two, even though we have half the faculty of many of the next universities, we are still the most prolific group, and we are high up there. So Wisconsin is a great place to do research in programming languages. So enough with the bragging. Let me tell you what we do. So because we want to help people write software that does the thing they want it to do, we work on three things. So one is verification. So we want to detect unintended behavior. So we want to help people find what's wrong with their software. We want to help them fix it so we can repair their software automatically. So we can try to synthesize small changes that make the code have the intended behavior. And more generally, we can even try to synthesize from scratch code that meets their intent. So instead of you programming something, you can tell us at the high level what you want to do, and we will magically find out the program that does it for you. And all of these is in the lens of what is called formal methods, which are basically the mathematics of computer science. So I'm going to give you kind of like now a brief tour through some of the projects we have been working on. So in verification, as I said, the goal is basically we have a program and we have some specification, so something we want to hold true for the program. And the program verifier is something that spits out yes and tells us a proof that our program meets the specification. Let's say, to be concrete, your program will never throw a null pointer exception. Or it says no, and it gives us a bug. So this tool is, a program verifier is a very useful tool for detecting bugs in your software or for proving that your software does not have bug. And when I say proof here, I mean a mathematical proof. And let me give you some examples of some of the verification that we do at Wisconsin. So Tom Reps, for example, he's been working a lot on verifying computational complexity. So he has tools where one can give, let's say, a C program and some property like I want this program to run in O of n log n, and he can prove whether this program runs or doesn't run in n log n. And this uses very cool techniques that I cannot explain in 5 minutes, but basically he creates some cool equations, and by solving those equations, you get complexity bounds on the program. So it's very interesting work. Another example of verification we might think of is the example I gave you before, where I have a neural network. Let's say think of it as a program that decides whether somebody gets a bank loan or whether somebody gets parole. And then we have a specification that says the outcome should be fair. And again, I'm not going to say much in this short talk, but there are many formal ways to define some notions of fairness we might care about. And Aus and I have been working on this problem, and it's basically you want to end up proving some kind of probabilistic properties of the program, and these properties kind of boil down to making sure that the program you're analyzing have some fair outcome. And we use techniques in probabilities and verification. So it's verification also applies to very unusual domain that maybe you're not used to. So Aus and Justin have been working on verifying differential privacy. So if you don't know what that is, so basically imagine you have a program that queries a database, and you want to make sure that the query cannot leak data about you. So let's say I'm asking how many people are there in the database who own a Prius. And it turns out that even when you ask these very generic questions, you can sometimes leak data about individual people. And Justin and Aus have come up with very interesting ways to combine ideas from probability theory and verification to verify this type of programs. So basically, you will give them a query that accesses some database, and they will magically check whether it's private or not. And more in general, Aus, Somesh, and I have been working in this field of neural network verification, where you have some neural network model, and neural networks, I claim here, they're just a special type of programs. And we verify some properties of them like robustness. So for example, in this example here, imagine that you have a neural network that takes as input an English sentence, like the house is nice, and you want that all these similar sentences result in the same outcome. In this case, let's say that we're predicting whether the sentence is a positive one. So all these sentences should be treated the same. Can we verify such a property? Okay. So I'm going to briefly switch to synthesis, which is the dual of verification. And so in verification, as you saw earlier, we are given a specification, a program, and then we give a yes, no answer. In program synthesis, it's kind of, we don't get the program. We only get an easy to write specification. And we have to automatically produce a program that meets the specification plus a proof that it meets the specification. So essentially, think of this as like, I don't even want to program. I just want to tell my tool that my program should do a certain set of things that I want. And in some cases, it might also be possible that there is no program that does the thing you want. But let me give you some examples, because I think it's a lot easier to understand for examples. So let's use again the domains we mentioned before. So we say debugging is an important problem. So a synthesis problem is to automatically generate fixes to your program that remove the bug. Okay. Another example is like, instead of writing a network that might create an outage because it has a bug, why don't we synthesize automatically configurations that are provably will not cause any outages? And similarly, instead of writing a bad program that then is biased, can't we just synthesize a program that is guaranteed to not have this bias? So it's guaranteed to satisfy the fairness condition. And in all these problems, you can add interesting objectives. So maybe you want to find the simplest bug fix. Maybe you want to find not any policy compliant configuration, but one that is robust under failures. Like if one node in the data center fails, your whole network will not go down. And similarly, if imagine you start with a biased program, maybe you want to fix it and find one that is close to it, but it is unbiased. And I'm going to show you some of these through some examples again. So for example, actually this is work with Aditya Kella, and sorry, I forgot to put it in on the slide, but our student Kaushik, he did a lot of work on building tools that take network policies. So these are things that network operators can write very easily. And we automatically generate configurations for the networks. And these are programs that are provably robust to failures. And in this work, we were able actually to generate configurations for things like the Azure data center. So we're talking about, so these are not, this is possible. It is possible today to synthesize programs that can scale to very large applications. So in the application I said before, let's say you're giving us a biased program, that one that has a problem, like it seems like it's discriminating and some definition of bias, and we can magically come up with an unbiased version of the program that is closest to the original one. And here again, I mentioned before, we use a lot of techniques from logical reasoning, and we combine actually techniques from programming languages, with techniques with learning theory from the machine learning community. And Tom and Somesh, they have this project on deploting software, where the idea is that you get some complex software that is very big, and you can synthesize some simpler representation of that software that maybe can fit on your phone. Because the problem with software bloating is that, like, these days we have, everybody uses all these packages, and we get the software is in a very large footprint. And so the idea here is that they could collapse software into simpler one. And Tom and I recently have been working on this idea that instead of solving synthesis problems separately, can we create a unified framework that can solve all the synthesis problems? So imagine, instead of, in what I showed you before is like, oh, we wrote one paper on synthesizing this, one paper on synthesizing that. Can we write one technique, one single format that will handle all the synthesis problems going forward? And this is one of the projects I'm more excited about these days. So to conclude, software is pervasive, keeps changing, and programming shouldn't be painful, but we need to adapt to the new type of software that is arising every day. And the only way we can do that is, I argue, is with this thing called formal methods, which is fancy logics, because it's the only formal language that guarantees us that we will not have mistakes and we will not have bugs. And if you join the MedPL group, which is these people, you will get to work on some of these cutting edge problems and help people build tools that will help every programmer make sure that their software doesn't have bugs and meets their intent. And so that's it.
Thank you, Loris. We're going to have another break now after all these research talks, and resume at 11:30. But before you go, students, please, I just want to make a few announcements about the schedule. So this evening, I'll have a Q&A where you can ask just anything you want to know about our grad program, and that will be at 6:30, and that'll be followed by the student perspective. So that will be.
Did you manage to make?
I did. I paused it.
And that we seem to be toggling back and forth.
Yeah, I paused it when you started making announcements.
Okay, so now next up is Wuhang Zhao, representing the Human-Computer Interaction Group at Madison.
Can I start now?
Yes.
Oh, cool. Thank you, Angela. Hi, everyone. My name is Yuhang Zhao. I'm an assistant professor from the Department of Computer Sciences. And I want to talk about what type of HCI research we have been doing at the University of Wisconsin-Madison, especially at the CS department. So first of all, what is HCI, right? So HCI research focuses on studying, for example, how people use computer technology, all the phenomena around people, the interaction between the computer and the machine, and also how we can design novel technologies and interfaces to better support the interaction between the human and the computer. And here at the University of Wisconsin-Madison, we actually have a very strong presence in HCI and design research. And you can see this is our the homepage of our HCI plus design research group. And we have many great researchers from different departments that are doing HCI related research. So besides computer science, we have iSchool, for example, and also industrial and system engineering, psychology, learning sciences, communication, and so on. So we have a lot of faculties and also many research labs that are relevant. So if you are going to join here, I'm sure you're going to have a lot of great opportunities to collaborate with these professors and also work on HCI research. And specifically at the computer sciences department, we have 3 professors working on human-computer interaction, including Professor Bilge, Professor Yeso Kim, and also me. So I'm going to talk through the research from each of our labs so you can have a better idea what research we have been doing here. And also beyond the individual research I've been doing, I would say, you know, our department and the university is supporting a very collaborative research environment. So besides, you know, our own independent research projects, we also have a lot of collaborations with each other and also cross department. So I'll start from my lab. So my research focuses on accessibility, which means I'm designing technologies for people with disabilities, and also augmented and virtual reality, plus mobile interaction, and also a little bit of human-centered AI. So I'm going to talk a little bit about some major directions in my lab. So first of all, part of my research focuses on exploring the experiences and the needs of people with diverse abilities, and also design and build intelligent interactive systems to enhance human abilities. And specific examples could include how we design and build AR systems to enhance the visual ability of people with low vision. So I'm going to show some concrete examples. For example, this is an AR system that we built called QC, which is designed for people with low vision, and we want to facilitate a visual search task for people with low vision. So here is a demo. With this head-mounted display, the user can just speak out the name of the target product that they are looking for from the shelf, and then the system can render different visual cues to attract and orient the user's attention so that they can easily find the target.
Look for pea snack. Look for onion rings. Look for pea.
And this is another example about how we design projector-based AR system that can help low vision people better navigate on the stairs. You can see that we are trying to projecting lights on each edges of the stairs so that low vision people can better see the stairs and navigate more safely. And another important perspective of the research in my lab is to address the accessibility of different types of emerging technologies. For example, how we can make the virtual reality technology more accessible for people with visual impairments. So this is one example where we designed a system called Seeing VR, and we created 14 different low vision tools that can be integrated into any virtual reality scenes to make the scenes more accessible for people with low vision. vision, for example, magnification or edge enhancement, and also it can include some OCR text-to-speech technology, text augmentation, and so on. So this is a demo video showing how these different tools can be incorporated into a post hoc plugin, so that all different very popular VR games can, use these augmentations so that low vision people can have equal access to them. So you can see this is a magnifier incorporated into Words of the Wizard application. And the edge enhancement is very powerful when the scene is very dark.
Solo. Party.
That is text to speech, and also a peripheral remapping. So besides these directions, actually, as I said, we are a very collaborative environment. So I also have several ongoing collaborations with professors inside of our department and across the departments. For example, I'm working with Ece on how we can make the visualizations more accessible for people with visual impairments. And I'm also collaborating with researchers in the security group to explore novel authentication technologies for AR glasses. And across department, I'm also planning to collaborate with Dr. Sambrita Model, who is a doctor in the Department of Ophthalmology and Vision Science. So we are planning to work on something together, new technology together for people with low vision. So beyond my research, I also want to talk about the lab of Professor Bilge. So his research focuses on human-robot interaction, and there are a lot of exciting research going on in his lab about how to build novel robotic interactions with humans. So for example, this is the work that he's been doing about how to design educational robots to study long-term interaction with robotic technologies. And this image is a learning companion robot that Professor Mutlu's team has built that helps children to read. And another example is his collaboration with the professor from our PL group, where they build design and programming tools that use software verification and program synthesis methods to make robot programming much easier. And this third example is about a project that involves collaboration. It's still a cross-department collaboration, which involves a collaboration with the psychology department, where they build a system that explores different ways of making the agents emotionally more sophisticated by designing algorithms and interfaces that are inspired by different psychological theories of emotion. And at the end, this is something Bilge and we are planning out, is we want to start a new project on exploring how to use AR-based interfaces to control and interact with robots. And this image you are seeing is actually an early prototype from his lab, where they built a tablet-based control user interface so that people can use this to program and control a collaborative robot to perform complex manipulation tasks. And the last but not least, we also have Professor Ece, who works on human data interaction. She is also here today, so I'm going to hand the stage to her so that she can talk a little bit more about her research.
Great, thank you. So nice to meet you all. I'm a faculty here at HCI Lab. My research focuses on improving the human experience when they interact with data. So next slide. So specifically, I'm interested in building interactive tools to help people understand data and uncertainty. So I've been working on a couple of projects that using analogy to contextualize complex concepts. So let me unpack what I mean by analogy in a few slides. So next slide. So this is a tool that I built that getting the user's locations and automatically detect the spatial measurements in online documents such as acres and kilometers. We often don't know how big they are, how small, how short they are. So to re-express those measurements using some of the landmark near you. So for example, this 73 kilo can be re-expressed as 2 times longer than the distance between you and Snoqualmie Fall, which is very famous fall in Seattle for the user who lives in Seattle. So please play the video. So first detect the measurements and then re-express the specific measurements in terms of like where you are for the area that you're familiar with and so on. All right, so next slide. So not only just the measurements, but similar approach can be applied to help people understand other statistical notions. So for example, effect sizes are a concept that captures outcome variability. So let's quickly think about a study where scientists give one group of people green tea, the other group people nothing, to check if how effective the green tea to reduce the bad cholesterol. So imagine 2 separate, very different experiments here. One on the left shows that the green tea group significantly overlapped with the control group in terms of lowering cholesterol, versus the right side of hypothetical experiments, there are less overlapped. So in this left experiment, the effect size is small, and then right side, the effect size is medium, even though the mean of the two, the average effect of 2 experiments are the same. So this is what statisticians call effect size, so how their outcome very varied. The question here is that how can we communicate this measure to end user? Can people understand what small or medium means, or should we even present it like standardized measures like Cohen's d 0.3 or 0.25? How can people know about that? So instead, in this project, I'm looking at the analogy to re-express the effect size. So for example, the small effect size can be re-expressed. This is equal to the probability that the randomly selected 16-year-old girl is taller than a randomly selected 15-year-old girl. So contextualized based on the analogy will help people understand this complicated measure. So next slide. So I'm designing systems that improve data communication by thinking of users' context and by leveraging strategy they're familiar with using. So these types of systems becomes essential as many AI model will deploy in the real world. There are needs to communicate uncertainty to the end user. So for example, we often rely on the model's predictions when we evaluate the listed house price is a decade or not. But the model's prediction always entails some uncertainty. So how can we communicate those types of uncertainty here in the form of like confidence interval in this case to the end user so that they can make a better decision? Also, let's think about the self-driving car. Probably the model that drives the car will produce lots of uncertainty measures for the current and the future situation. How can we communicate this uncertainty with the end user so that they can make some timely, rational decision? Next slide. So here are some ongoing collaborations. As Young mentioned, we're working together on the visualization accessibility. I'm also collaborating with Sharon Lee, who's faculty here, working on a deep learning to see if visualization analytic tool can help detect the out of distribution instance as well. That's all. So please feel free to reach out to us if you have any questions.
So next up, we have Michael Gleicher.
Let's see, how am I? Hello.
There you are. Hi.
I'm there. All right. Hi, everybody. Let's see if I can share screen. Was it the screen 2? Share. Oh, but now I don't see. I don't see what you see anymore. So hopefully, do you all see a slide? I also don't see the chat. So I have no idea if so. I don't know, Angela. If somebody asks a question or something, let me know because I don't see the chat. But
should be across the bottom of your screen if you.
It's not because my screen
Okay.
went into sharing mode.
We'll let
it
you
should
know.
be. Let's not talk about what it should be. I'll tell you what it is. So hi everybody. I'm Mike Gleicher. I'm a professor in the department. I am going to talk about visual computing. We used to say, oh, it was graphics, but it's not just graphics. In fact, I'm not sure, maybe is any of it graphics. So I'm going to talk about I'm speaking for myself, for Professor Eftichios Safakis, and for Professor Yesol Kim, who actually you just heard from. So well, I'll say more about what she has to say. So this whole thing of visual computing, what is it? I told you it isn't just graphics. Basically, this is a catch-all for things that didn't fit nicely in other groups. Historically, graphics was a sort of a set of us who thought about a wide diversity of things, and we needed to put ourselves somewhere. So we kind of organized around this idea of visual computing. So there's a bunch of us who do things related to graphics, to data visualization, to simulation, to animation, to robotics. Now, some of these things actually got talked about before. So actually, vision is coming up, but you heard about robotics, you heard about virtual and augmented reality, you heard about human-computer interaction. A lot of this has a visual element, so it's not that that isn't visual computing. So more about it, it's more about who. So I'm going to talk about the work of three faculty members, although all of us work a lot with others and people do related things. Yesol, who you just heard from, Eftichios Safakis, who works primarily in the area of some more traditional graphics in the areas of simulation, and myself. People who have spoke earlier and are going to speak, you've heard from the people who do HCI and virtual reality stuff. You'll hear about computer vision, Mohit Gupta and Youngjae Lee. You've heard about other robotics collaborators, Bilge Mutlu and Josiah. There are also people in other departments who do similar things. There are people in design studies who do augmented and virtual reality. There are people in mechanical engineering who do robotics. There are people in psychology who do perception. So all of these kinds of things relate to the kinds of topics that I'm going to talk about as well. So in a sense, people talk about a lab. Well, to me, a lab is a space. And one of the things which is kind of interesting about the way that we work is we tend to like to put people together into a into a shared space where we have a big room where everyone kind of can work together, even if we're not working on the same thing, so we can share thoughts and ideas and collaborate. If you were in the building, you'd see we have a big room centered around 13 on the first floor of CS, and a second room where we have robots. We have our offices up on, the faculty have their offices up on the 6th floor. I'm not sure Yesol has even been to her office yet. All right. So we have a room, the main lab, and then we also have the sort of a room where we keep robots because, well, robots like to have their own space. All right, so to talk about what the individuals do, I just you just heard from Yesol Kim. So Yesol is a new professor in the department, and she works broadly in the area. I would try to say better than just more specifically than just human data interaction. She works on decision making. How do we help people make decisions in a better way? So in doing this, she explores trying to understand how people make decisions. In particular, if there's a decision, if it's hard to make a decision, that means there must be some uncertainty, because that's what makes decisions hard usually. And then the question then is, well, how can we use information and how can we take data and have that inform the decision-making process? So one of the interesting things about her work is that for those of us who work in the field of data science or visualization, we typically think we have data, we have a visualization, you show it to a person and that implements it, right? They interpret the data, they make estimations from it, and they make decisions. But one of the things that Yesol brings to this is the observation that, well, no, actually, people bring a lot of other things to the party here. So people bring their own knowledge, their beliefs, their prior expectations, their goals. They bring all this to this process of interpretation, estimation, assessment, and decision making. And by understanding how people do that, you can do a better job at helping them. So in her work, she builds models and tools that help us take what the user believes ahead of time and brings us into that process of data understanding and decision making. So this process, through this, she built up a model of how people think and how we can try to understand, based on what you already know and what you already believe, what do we need to show you to enhance, to better get you to be able to make decisions and be better informed based on the data. So what she does is build systems that both get from the user, this is what I already believe, and use that to inform how we design, how to present more information to the user so it can help them in the most effective way. So she also, she mentioned this before, she works on accessible visualizations. It's kind of a, I don't know, an oxymoron of saying, well, how do you help somebody see something if they can't see? This is a kind of an interesting question. And, is even visualization the right word? How do we present data in ways that are not necessarily visual? Because if somebody is visually impaired, a picture isn't really going to help too much. And then also, well, she actually showed exactly these pictures before, so she described it better than I can probably. All right, so then I want to talk about Eftichios Safakis. So he is around. He will be available to meet with you this afternoon. If you haven't scheduled with him, send him a note, or that goes for all of us. We don't hide very well. So Eftichios's focus is on how do we make models of the physical world. He cares about how objects in the world function, how they look, because by understanding how things in the real world looks, then we can try and simulate them. And for simulation, there's sort of two pieces. One is how do we make it be more accurate and more correct and capture more phenomena, but also the problem of how to make it faster and scalable. How can we use the fact that we have all these fancy, cool, and weird computers to actually perform these computations? So a big component in his work isn't just coming up with the math and the physics behind the way the world works, but figuring out how to use modern parallel processing, things like GPUs and memory systems in multi-core processors to make these computations much more efficient, accurate, and scalable. So some examples of the kinds of things he does. He does a lot of work in trying to simulate humans. So how do you make muscles that actually behave like real muscles so we can predict what will happen? He did work on virtual swimming. Now, of course, if you can simulate humans, you can simulate animated characters, which is good if you want to make animated movies. Now, but in addition to the sort of the fanciful stuff, there's a big application of trying to do virtual surgery. That if we try to simulate what happens in surgery, that can both be useful for surgeons trying to plan what will happen, but also in terms of surgery education. The thing you see in the lower right is a bunch of medical students trying to learn about surgery by playing with a simulation. All right, so he works on how do we simulate all kinds of different physical phenomena. When the geometry gets hard and complicated, this gets really interesting. One of the projects involves how do I take very, very complicated shapes and figure out how to plan how they will behave when we try and manufacture them. Another thing that he works on is how can I use observations of the world and create models that can be driven by these observations. So here you can see he's covered his face with markers so he can track observations of his face and then map it to a physical model that will be driven from his actions. Now, this work that he does, you can see it says Disney down here, but a lot of his work is done in conjunction with movie studios, both in New Zealand and in sort of the Western Hemisphere, to try and figure out how can we use these better models to make movies. Okay, and then there's me. So for me, I work across a whole bunch of things. I've been said I have academic attention deficit disorder. It might look like I do, I work with robots, I work with human-computer interaction, I work with graphics, I work with data. But for me, the whole thing that ties it all together is I care about how people work with complicated things. And for me, generally, it's going to be something visual involved. So I care about how we work with graphics, how we make pictures, how we work with data, how we draw understanding and meaning from data, and robots, because, well, I like robots. So for creating graphics, we build tools to try and make it easier for people to create animations and pictures. We work on tools that make it possible for people to automatically produce and for either automatic production to produce good quality video from the kind of video that you just capture. So in this project, we took just a camera that was taking a picture of a play going on a stage, and it automatically built up close-up views and more cinematographic things that made it much better to watch. In the area, most people say data visualization. I prefer the term human data interaction, because what is really interesting isn't just making it so you can see things, although that's a big part, is how do you help people work with data more broadly? In this, our work involves research, developing new methods. We actually build tools that help people work with data. And then part of our mission as well is, how do we help other people do this? And how do we help people make good choices when they develop visualizations? So our work here involves doing perceptual science, understanding how people see, using that to inform new techniques that present data in interesting ways, using this to build systems that actually help people do things, and then going back from those systems and say, well, what did we learn? What are the principles that we can establish from that? We work helping collaborators in a lot of different domains, helping people who do analyze literature, people who work in genetics, biochemistry, virology. We build systems that help that work data science. A lot of what we do is to support the work of people building machine learning systems. For example, we build tools that help people when they're designing classifiers to make comparisons between classifiers, to diagnose how their machine learning systems work. We've built systems that help people find new data and bring new data into their machine learning analysis to improve performance by adding extra data. All right, so visualization then also ties to robots, because we talk about robots. So we do visualize the robots, but more often when we're doing robots, we think about real robots. We do have some cool real robots. This particular robot is in the lab. It's kind of lonely. So if you come, hopefully we'll be back in the lab so you can play with this robot. Earlier, if you were at Bilge's presentation, he showed how we do work on how people control robots. One of the things I like to say is we try to make dumb robots to help smart people. A big piece of controlling the robot is helping the person who's controlling it understand what the robot is doing and see the environment around the robot. So a lot of what we're working on now is, how do we figure out how to show what's going on with the robot so that people can make decisions in controlling it? Another aspect of showing people what's going on is feeling it, because a lot of what robots do is touching things. So we've built this knob connected to a motor so we can provide different sensations to people to try and understand how do people react when they feel different things. And we're interested in how can we measure what people are doing, because if we can measure what people do, then maybe we can use that to show a robot how to do it as well. Okay, so I think I've pretty much run out of time, but in the last -1 minute I have, I'll say there are a whole bunch of classes related to this. So if you come, you can start out both working with us on these kinds of questions, but also to take some classes like computer graphics and data visualization, and a bunch of newer classes that will give you the basic elements to build up so you can get involved with these kinds of projects. And with that, I'd like to thank you for your time and attention, and please reach out to us if you haven't scheduled a time to meet with any of us. We'll find another time to meet or to join anyway. So thank you.
Thanks, Mike. Next up is Mohit Gupta from the Computer Vision Group.
Thanks, Mike. Hi, everyone. My slides are not going to be as polished as Mike's, but hopefully I can give you a flavor of what we do. So first of all, normally I would have said welcome to Madison, everyone, but this is an unusual year. So for now, I'll just say congratulations, everyone, on being admitted to our program. I thought I'll give you guys a very quick overview of what we do in computer vision here. So let me share my screen. So I would first maybe try to make this a little interactive and start by asking you guys, what do you think what computer vision is? Any guesses? And some of you may have maybe taken some courses perhaps earlier or seen things, heard things. But what is computer vision? And feel free to type your responses or maybe unmute yourself. Yeah, image recognition is a pretty good answer. Recognizing and interpreting visual scenes, exactly. And the thing is that if you ask different people, you will get different answers. Somebody would say, yes, the goal here is to recognize things, interpret things. If you ask somebody who does computer graphics, they would say computer vision is nothing but just inverting image formation, right? In graphics, we go from 3D to 2D. In vision, we try to do the other way around. We go from 2D images and try to infer the properties of the 3D world, right? So the bottom line here is that, although we may not agree on what computer vision really is, but what we can agree on is that it's really useful. There is a lot of applications right now. Computer vision systems are now heavily deployed in our industries, in factories, in libraries, vehicles, roads, surveillance systems, malls, almost all indoor spaces, public indoor spaces for surveillance, cameras, of course, social networks, something as mundane as a vending machine, almost all kinds of user interfaces. Think about a mouse, think about your phone. There will likely be a small computer vision system running somewhere, right? Entertainment, gaming. Mike talked about HCI, special effects, right? You saw this picture of FTQs with the markers on his faces. To go from those markers to a virtual character, again, there will be a computer vision system somewhere being used, right? Poster child application of vision these days is autonomous cars. These systems are now making their way to space robots, remote sensing. They're now being used in our bodies. So I would say right now there's almost a kind of a computer vision revolution going on. There's a lot of interest in academia, also in industry, in computer vision. I would say right now vision is probably one of the fastest growing fields in academia and also in industry. So good time to be doing computer vision. So fortunately, we're starting to build a fairly active vision group here at Madison as well. So I'll start with Professor Yongjae Lee. He will be joining us in fall of 21. And he does a lot of work with building computer vision systems with minimal human supervision, right? Right now, he also does stuff with privacy preserving recognition, object detection, segmentation. He publishes a lot in CV and ML venues, all top venues. He's right now spending time at a self-driving car startup. But I'm not sure if you have been able to schedule time to meet with him. But if not, feel free to reach out to him. Then there is Yin Li. He is primarily in biostatistics and medical informatics department, but he also has an affiliate status in computer science. He does work with wearable computers. Whenever you have systems which you can wear, so what we call egocentric vision, we start coming across some interesting problems, right? So can you use these kinds of systems to understand your behavior, understand your activities? And are there any health biometric implications which you can, which come about from analyzing these wearable sensing data? So he looks at a lot of his wearable sensors. yeah, so this is just a quick snapshot. He has been looking at these wearable sensing systems for analyzing activities, analyzing gestures. How do these videos interface with language? Doing stuff like hand tracking, etc. Again, as soon as you kind of turn around the camera from looking inward to you to looking outward, there is some interesting things that happen. So he looks at a lot of these things. Then there is Vikas here, not this one. So he does a lot of computer vision and statistics stuff. In particular, he looks at applications of vision and machine learning for medical data. More recently, he has started looking at the issue of fairness in vision systems. So here's an example. The idea being that you would want a vision system to zoom down on the right features for a given task. So here, for example, the task is activity recognition, and you would hope that the system picks up on the relevant features here. For example, here, not the hair, but the objects in the scene, the steering wheel, to determine that this action here is driving and not cooking, right? And these fairness issues are becoming more and more important as we start looking at ethics in vision and AI. So he looks at a lot of these aspects. And of course, as I said, he looks at their implications, not just in general settings, but also in medical settings. So if you're interested in medical applications, it'll be good to talk to him. Finally, I'll talk a little bit about what I do. So I work on imaging aspects of vision. We look at designing new kinds of cameras, which hopefully can give you some capabilities and functionalities that would otherwise be impossible. So just as an example, we have so recently been looking at this umbrella of methods called extreme imaging, where the goal is to image some phenomena or objects that would otherwise be invisible. So one example is, let's say there's a 3D camera. The 3D camera is, one example is LiDAR, which recovers the 3D geometry or shape of the surroundings. Let's say camera is looking at something which is very far away, something like this. With a normal camera, you would expect to see something like this. You can maybe make out that it's a face, but maybe not much more. But what we are now trying to do is, can we go much beyond this qualitative inference that this is maybe a human face to getting something like this, where maybe we can now start recognizing the person. So it could be a qualitative shift. Another thing that we have looked at is designing cameras or vision systems which can detect very small motion. Imagine being able to detect somebody's pulse from a long distance, right? You can imagine there'll be could be some interesting biometric security application, maybe even some health applications. Can you do some remote health monitoring, right? So I just wanted to show an example. Here we have one of our cameras looking at a piece of chalk. And this is a video here. It's a very boring video because it seems that nothing is happening. But actually this piece of chalk is moving by a very tiny amount, about a few microns per frame, so very hard to see. But we designed this different camera, which looks at the same scene. It captures something like this now on the right. It looks like noise, garbage at first, but the key thing here is that this is moving very fast, which means that now we can design vision systems to recover this small motion. This picture of the system, but I want to show this example. So what we did was just to demonstrate this. We got a stopwatch. We painted it all black except the 3 hands. And what we wanted to see was whether we can track the motion of these hands. Now clearly the second hand is easy to track. We can see it moving. But the minute and the hour hands, we didn't know whether they even moved on a per second basis. But it turned out that with this micro motion detection system, we were able to track, sorry about that, we were able to track the motion of these, even the hour hand, on a per second basis. It turns out that it does move very minutely by like less than a 100th of a degree per second, but we are able to track it now. So this was just a fun demonstration, but of course there are implications in, for example, gesture recognition. Can you now track very small, minute gestures so that now you can maybe start interacting with devices without having to wildly wave your hand by doing some minute subtle gestures, right? So it's just an example system. For example, we had this thing where just by small motions, we can start detecting gestures like horizontal stretch in this case, maybe a swipe down function, etc., etc. Then we started asking question, right now we can maybe recover a lot of fine details, we can recover small motions, but can we take this a step further? Can we start looking around the corner? Now this may sound like science fiction at first. How do you start recovering properties of something that you cannot even directly see? Now the key idea here was that yes, we don't get any direct light from this object, but we do get light indirectly after multiple bounces. And if we design the right kinds of algorithms, we can start recovering some properties, right? So I just want to show an example here. Was a schematic of a lab setup. Here we had a couple of objects moving around the corner. Again, notice that the camera is not directly seeing these things. There's a couple of pieces of chalk here, just for demonstration. They were moving on a robotic stage, but we were able to recover their individual motions around the corner now at a very fine scale. Yeah, and then there are other things like we also work on building cameras and vision systems that work reliably in the wild in challenging conditions. Like now you want to design vision systems which work in challenging outdoor conditions like for autonomous cars, for difficult geometry, materials, etc. Some examples here. We have built 3D imaging systems for really challenging scenarios, which now, of course, have in a satisfying way practical implications. These are now being deployed in several industrial settings. So that's a satisfying thing to see. So overall, yeah, vision is fun. It's a highly interdisciplinary, quite challenging at first, but once things start working, it's actually quite satisfying and fun to watch. So I'll stop with that. I actually finished 2 minutes early. So I can maybe take those 2 minutes to take questions, if any. Any questions? I will be available to meet later in the day. And I see that some people have signed up. But if you could not find a slot, then feel free to reach out to me and we'll find some time. So the question is, do we make these devices yourself? We, as much as we can, we try to maybe buy some off-the-shelf components and put them together. Sometimes we come up with a design which we cannot manufacture ourselves. It requires something more involved. Then we go to our collaborators in physics and electronics. Is there anyone here doing research in particular to remote sensing? Maybe not particularly on that application area, but we do develop techniques which could be broadly applicable. For example, if you want to build an object recognition system on remote sensing images, you could probably start with a more general object recognition system and see whether you can adapt to a remote sensing application. Yeah. What percentage of moving body can the cameras that look around the corner spot? In terms of percentage, actually, you can recover the entire body. Now, I think another way to ask this question could be, what is the resolution at which you can recover the body? Can you recover very fine details? So the answer is right now, we cannot recover very fine details, but you can maybe distinguish certain actions, like maybe somebody doing jumping jacks versus maybe somebody walking. So that level of detail we can recover right now. Mm-hmm. And again, I'll be happy to talk more about these things when we talk one-on-one later. Yeah, thank you. Thank you very much.
Thanks, Mohit. So our next speaker is from the theory group. And Christos Samos.
Great.
Thank you, Angela, and thank you, Mohit, for the great presentation. I'll talk to you about the theoretical computer science research that we do here at Madison. And let me find my great. Yeah, so first of all, what is theoretical computer science? In theoretical computer science, we study the fundamental capabilities and limitations of computing. In particular, we ask which tasks can be solved and what is hard to achieve and how efficiently can you solve certain tasks versus others, and what algorithms you can create. And every time you're dealing with these new objects like parallelism, randomness, like quantum computing, quantum interference, what essentially can be computed using this power, and how that power differs among different computational models. And there's a lot of emphasis on provable results, so there's a lot of math being involved in this area. But it also has a lot of applications, in particular in economics, in machine learning, in networking, in cryptography. So a lot of research that we do here has these types of applications. And it's a really interesting area to be at. So it's very fun because you get to work with like extremely challenging problems that are like fun, like puzzle solving. But it also helps lay the foundations of computer science. And you can see this if you look at the Turing Awards. There are a lot of them given in theory for their groundbreaking foundations and groundbreaking results that they have contributed. And yeah, so there are a lot of recent advanced technology, science, and mathematics that like theory exploits to obtain these results. And of course, it is benefiting society. We can study how we can obtain more efficient markets, how we can do fairness, privacy, kidney exchange, epidemiology, and a lot of interesting areas can be modeled theoretically, and you can actually prove interesting results that can be used for practical systems. And there's a lot of faculty in the theory group, and I'll talk about the research next. But we also have a large number of theory students. I think currently we have about 15 PhD students, and our alumni have taken great positions in industry and in academia. So they are researchers at Google, at Microsoft Research, at IBM. So you can take a path doing industrial research, but you can also, there are a lot of alumni in top universities around the world, and some of them are current graduates, are postdocs in top places. And also students gain a lot of prestigious awards, and you can check our website for more details. So even if you're not even if you're not one of the become interested in becoming one of the theory students, we offer a lot of interesting courses. We have undergraduate courses, which are Introduction to Algorithm Theory Computing, Introduction to Computational Learning Theory, and we have some graduate classes that you will probably enjoy taking: Advanced Algorithms, Computational Complexity, and Arithmetic Algorithms. But we also frequently offer a lot of topics courses to stay up to date with the current advances in theory. So these are some topics we gave in recent years, like quantum computing, advanced learning theory, approximation and online algorithms, algorithm game theory and machine learning, complexity of counting problems, algorithms for massive data sets, beyond worst case analysis, and pseudo-randomness and de-randomization. So these are rotating topics that are given by our theory faculty. So I can now speak more about the research of individual faculty. So we have many great professors here. One of them is Professor Eric Bach. So he's one of the top researchers in number theory, algebra, and combinatorics. So he does a lot of, he's using a lot of analytic number theory, algebraic geometry, and classical analysis to understand how prime numbers work, how you can factor numbers, and how to design cryptography based on number theoretic methods, and has applications in computer algebra, pseudo-random number generation, and quantum computation. So he's also the author of this book on algorithmic number theory, and he's a well-established person in his area. Now, we also have Professor Jinyi Tsai. So he's interested in computational complexity theory, and in particular, he's an expert in the theory of counting. So every time you're dealing with a problem that where you need to count how many solutions there are, these can be classified into different, in essentially two different classes, whether they are solvable in polynomial time or whether they are hard. And so Jinyi offers, has provided a lot of characterizations and dichotomy theorems for understanding which problems are easy and which problems are hard. And he also has a book on this topic, on these complexity dichotomies for counting problems. And yeah, so a lot of his research, and he's very actively publishing in top venues like Fox and Stock for computer science. And he's also looking for students. And so a lot of his work is about understanding how many solutions are there to a certain combinatorial object. So these have a lot of applications in theoretical physics, and he studies like these Holland problems and how many ways you can have, how many graph homomorphisms there exist, and gives these nice dichotomy theorems for classifying the complexity of these problems. We also have Professor Ilias Diakonikolas. So he's a top researcher in algorithms, learning, statistics, and applied probability. And he's famous for his work on high-dimensional robust statistics and learning, non-parametric estimation, and distribution testing. So his work essentially lays the theoretical foundation for many of problems in machine learning, and how to deal with machine learning systems when your data have corruptions, noise, and how do you remove them. And so he studies the trade-off between statistical efficiency, what you can actually learn but with the data that you have, and how you can do this efficiently, whether you can actually build efficient algorithms that achieve these theoretical limits, and for many fundamental problems in machine learning. So we work together a lot, and our students work frequently together. And he's a great researcher, and one of his of our work in notable work in recent years about robust estimation got like the best paper award at the New Rips in 2019. So we are actively performing research in these areas of robust statistics. Now, Then we also have Professor Van Melkebeek, Dieter Van Melkebeek. So he's also working on the side of complexity theory, and studies how to de-randomize certain randomized constructions, how to do polynomial identity testing deterministically, identifies connections with circuit lower bounds. And so essentially a lot of his research is understanding what are the complexity of certain problems. For deterministic problems, randomized algorithms. And recently he's also very interested in quantum computing and quantum machines. So he's offering frequently this class on quantum computation. And yeah, so he's doing a lot of work on understanding the complexity, both on the classical computing, but also more recently in this quantum computing. Essentially, whenever you have a quantum machine, what can you do with it and what you cannot do. And finally, my research, I'm also working mostly on the side of algorithms and designing upper bounds for certain problems. So my work is a lot on algorithmic game theory and computational economics, how to design efficient auctions, how to design efficient economic mechanisms, and that enhance market stability and so on. And how do you design systems even without money that ensure fair outcomes. Also, I'm also, as I told you, I'm also interested in learning theory and how do you solve estimation problems in high dimensions. And my research takes concepts from both statistics and economics and tries to apply them to the complexity of the recent challenges in machine learning. And I'm also interested in beating the complexity of the problems, but more on the fine-grained complexity, which essentially tries to characterize what can be solved in polynomial time. And what is the best polynomial time, running time you can obtain for a certain problem. So this is all I had to say. So you can check our webpage for more details, and you can meet with us during our meeting. So a couple of notes. One is that I'm really sorry that I had to reschedule my today's meeting to tomorrow. So if I sent an email, so if people, I already saw that a lot of you signed up already for tomorrow. So that's great. And a second, so a note, if you want to talk to me, there are still some available slots for tomorrow that you may want to join. And another, Elias Diakonikolas also asked me, he was unable to sign up to actually add slots in his calendar because he just had a baby this week and his schedule is unpredictable. But like, please email him. He said to schedule like an individual meeting, and he would be happy to. Yeah, he would be happy to meet you. So that's all I had to say. Any questions?
Thank you, Christos. I just want to make a few announcements.
I'll stop sharing then. Great.
Okay, Cindy made the announcement in chat. That's fine. Thanks, Cindy. Everybody,
You can still verbally share with them.
Okay, well, basically, check out the schedule. It had a few updates this morning, and I hope to see many of you at the Q&A session this evening. I hope you enjoyed the talks and it piqued your curiosity about the research and your interest in working with our professors here at UW-Madison. So thanks all of you that joined us this morning. Hope to see you later. Take care.